Um, this morning we have a keynote by Amina Torlak. We're very glad to have her here. Let me tell you a little bit about Amina. She's a senior principal scientist at Amazon Web Services, affiliate professor at University of Washington. Amina builds new languages and tools for program verification and synthesis. She has a bachelor's, master's, and PhD from MIT. She created Rosette and CodCod, and is the lead developer for Cedar, which we'll hear about today. Rosette is a solver-aided languages that powers verification and synthesis tools. CodCod is a solver for relational logic, used widely in software analysis and design. Cedar, I'll let her talk about momentarily, but the main thing is that it's used in production all the time by Amazon Web Services. Amina is a recipient of the Robin Milner Young Researcher Award, an NSF Career Award, a Sloan Research Fellowship, and the AITO Dodd Nygaard Junior Prize. We brought Amina here because I had the chance to sit on a panel with her a year ago, and she gave a talk about Cedar, but we were limited to about 20 minutes. So I only got to hear a little bit, and I thought it would be wonderful, and you would all love to hear a longer version and hear about Cedar. Thank you.
And they talk about why you might need and want to do this course. The big part of it, the main part of it, is about how we design it. So appreciation is the problem of the tree. Each principle can perform one action in three of these principles. So anytime after the meeting today, you have to put it online banking, law practice account, healthcare, screening, all of them. All of them are single entity. Here, this is a source of there are lots of representation models that are well studied with test specific machines to protect sensitivity in our future. For example, right. Better? Okay. If you want to, for example, give access to users based on their roles within the organization, you will have role-based access to space. For example, managers can see their own employees' records. You can also decide to give access to users based on the attributes of either the user or the principal. For example, I can access all the servers that are in the same geographical region as I am. And finally, you can give access to resources based on the relationship between the user and the resource. This comes up a lot in documents, right? So I'm allowed to view documents for which I'm a designated viewer or the. So all this sounds good. We can do all these things. The characteristics of these models are well known, but actually implementing this at scale, you see new multimedia opportunities in identity. Turns out to be quite difficult. So to give you an idea for why this is hard today and how Cedar helps, we'll consider projects of the story application for sharing a to-do list or tiny to-do. And what it does, it allows users and teams. So here we have some users which are organized into teams to create and share to-do list. Okay, so I can create a list, I can share it with you, and you can edit the items, you can toggle them on and off, and so on. Now, normally, when applications, when you do an application like this, what people commonly do is that they will embed the authorization logic within their application code. So when I click on some web UI and ask the system to give me the contents of the list, or show me the contents of the list, something like this method is going to, Python method is going to call to the backend. And what this method is trying to do is it's trying to check first whether I'm supposed to have access or not. And then if I am, it's going to give me the content of the list. So what is this check actually doing? Well, if you stare this code hard enough, you will see that it's trying to say that users are allowed to perform the get list operation. So I'm allowed to view the contents of a list if I'm an admin, if I'm the owner of the list, or if I'm a reader or an editor of the list. Now, this is really hard to get right because what this code is doing is checking the negation of what I actually want to assert, right? And getting those things correctly is tricky, is probably one of the top speedy security errors that you will see come up in various security lists. This is also really hard to audit, okay? If you want to convince another person that you're implementing your permissions correctly, they have to analyze general purpose code. They actually have to view your applications to be sure that nobody who's not supposed to have access to a resource actually has it. And finally, this is difficult to maintain, okay? So if the permissions change, you actually have to recompile and redeploy your application. Now, a better way to do this is what we call policy-based access control. And the idea is to completely separate your authorization logic from your application logic. So at this point, your application is not going to change anymore, no matter how frequently your permission change. Instead, what you're going to do is you're going to have that one line of code at the top that consults an authorization engine, and this authorization engine evaluates permissions, policies which are written in a domain-specific language to determine whether access is allowed or not. So now you can share the same set of permissions across all methods that are implementing the action. So here is the first phase of Cedar. Here's what Cedar permissions look like for that mess of Python code that I showed you earlier, right? So you don't have to be a Cedar expert to see what this is saying. So the first permission here says, well, principals can, owners can perform any action they want on their own resource. The second one says, administrators, like you're a member of the admin team, you can perform any action you want on any resource that application planning to do. And then the final one says that you can perform this get list operation specifically if you're a reader or an editor of that resource. Okay. Now, Cedar is a relatively new authorization language as far as those who know. I've been out for about 2 to 3 years. It's open source. It is used heavily within AWS, 30 plus services and applications, as well as other tech companies, Cloudflare, MongoDB, Salesforce, to name a few. And interestingly enough, we are seeing wider and wider adoption for people outside of companies outside of this problem. So what's unique about Cedar, right? Why would you choose Cedar over any other authorization? Why did we build it? Well, we designed Cedar to find a new way to balance 5 criteria that we identified as desirable must-haves for this kind of domain-specific language, so an authorization. The first one is that your language should be autonomous. The people who are not programmers should be able to read, write, and understand policy involved, right? Because permissions are also given by the system, not necessarily programmers. The second one is that your language should be expressive enough to support common authorization models. So things like role-based access control, relation-based access control, and attribute-based access. The third one is that the language should be fast. So in so-called zero trust architectures, every time you make a request to do anything, an authorization check runs. So these things have to be really fast, and they almost have to be bounded and deterministic. The next one is that the language should be type safe. So I should be able to design a nice type system that doesn't have too many false positives, but that eliminates common errors quickly and statically as you write in your policy. The final criterion is unique to students and report and liability. What this actually means is that the procedure language is designed specifically to enable sound and complete reduction to a decidable fragment of the SMC logic. Because of this reduction, we are able to automatically prove that your policy spec satisfies accessing their small value. Okay, so that's the first sort of thing that's unique about CEDAR. We achieve this new balance of these criteria, specifically being able to ensure that the language is analyzable. So that's unique about CEDAR. The second one is that CEDAR is built to a high standard of assurance using a development method, which we call verification guided development. This development method involves building CEDAR twice, as you will see. Once in a theorem proving language called Lean, in which we prove all the properties about CEDAR that we care about, and once in Rust, that's the production implementation that runs, and then doing differential testing. So in the rest of the talk, we're going to cover all of these design goals, and I'm going to show you how we meet them. And then we're going to end by talking, by seeing how we do this verification guided development for CEDAR itself. We're going to start in the language design with a focus on expressiveness and ergonomics. So CEDAR policies have a very simple syntax. Each policy starts with an effect, which can be either permit or forbid. Okay? And they give you obviously. So permit gives you access, forbid takes away access. The next part is called the policy scope. And this is where we introduce these variables that we use within your policy. The principal action resource, you could optionally constrain the variables within the scope using the equals and in operators. So this in operator is really important and unique to CEDAR, and we're going to hear more about it later on. But think of it as testing the membership in groups of principles and resources that mentioned. Okay, and then finally, another optional element, you can have as many of these as you want, are so-called conditions, which are further constraining access based on the attributes of the principal resource action. Now, principal action and resource are what we call entity references. So they are names. So, and you can see what that pattern looks like. So there's a type of the entity, in that case, action, followed by an identifier of the entity that's unique within that type. So they are references to stored objects. Okay, so think of this as your application data or metadata that's authorization relevant. Normally, this sort of thing is stored in the database. Okay, so entities can be organized into an entity hierarchy, which is a directed acyclic graph, which groups the entities in a way that makes sense for your application and your domain. So for user entities, you might want to group them up into teams, organizations, regions, depending on what you're modeling. For resources, you might imagine, putting them into folders and different structures that, again, makes sense for the entity, for the resource. Now, in addition to having these hierarchies, you can also attach attributes to entities. And these attributes are, think of them as JSON blobs, except that we are using square brackets to represent sets rather than lists, and we're using braces to represent records. So you can have arbitrarily nested records, sets, strings, integers, booleans, and attributes can point to other entities. So what you can see here is that this list entity, its owner field is another entity, and its editor and reader fields are also other entities that point to these themes and people who can read and edit this particular list. Okay, so to actually evaluate a CEDAR policy, in addition to passing in the relevant entities, their hierarchy and their attributes, you will also pass in a request and to bind the policy variables to the appropriate values that you want to test. So here's an example. We're asking here whether this particular user Kesha is allowed to perform the get list action on the resource list 123 in this particular context. So context variable is not used in this particular policy. What it actually is a way for your application to use and store transient data. So these things are not fully data. Think of it as source IP address, current time, right? Whatever makes sense. If you have some transient data based on which you want to do authorization, you would pass it into other documents. Now, Given these inputs, the CEDAR authorizer will determine whether the request is allowed by your policies by evaluating the policies and maintaining these two invariants. Specifically, the request is going to be allowed if it satisfies at least one permit policy and zero, none, no permit policy. So that is the only condition, if and only if, under which a request is going to be allowed. Otherwise, it's going to be denied. All right, so to give you a concrete example, Kesha here is allowed to perform the get list action on the resource. And the reason is that she is a member of the temp team, and the temp team are the readers for the list 1 through 3. So this first condition in this policy is what gives her access. Okay. Here's another one. So the only thing I've changed now is I've changed the user from Kesha to Emma. Okay, Emma is allowed to access to perform get list on this list. Can she see the contents of the list? No. The answer is no, because Emma is neither an editor nor a reader of this list, because she is not either in the temp team or the intern team. So therefore, this policy doesn't fire it, and it is the only policy that I currently have in the system that's on the slide. So either is a default denial. There is no permit policy that fires, access is denied. To actually give her access, you have to write another policy that explicitly gives her access. So here's that policy. It says that principals who are members of the admin team are allowed to do any policy of this access. But here's a final example. The question now is whether the principal Andrew is allowed to perform the create list action on the timing to do application. Any thought? Is he allowed to do this? No, I see some shaking hands. That's correct. He's not allowed to do this, because even though he's an admin and the permit policy says yes, he can, this forbid policy fired. Right? He's not allowed to do it because he's a member of the SAM team, and members of that team are not allowed to perform this action. And in CEDAR, forbid trumps permit. So no matter how many things permit, even a single forbid fires, it's done. So this is an explicit denied, not allowed access. Now that you've seen the semantics, a little bit about the data model and the syntax and the semantics of CEDAR, we're going to briefly talk about how to use these constructs to express role-based access control, attribute-based access control, and then by combining the two, relation-based access control as well. So they are languages that are dedicated for relation-based access control. They have the concept of a relation. CEDAR doesn't, but you can still express it by combining role and attribute-based access control. So to express role-based access control, you actually just use the hierarchy on your entity. Okay, so you model your roles as groupings of principals, and what these policy tools are saying is they're saying that if the principal has the admin role, right, using the team admin, they're allowed to do anything. And if the principal is the team temp, well, they're not allowed to perform this team. Okay, the magic here happens with this in operator, which tests for transitive membership in the hierarchy. Okay, so it's actually testing directly. So what does that mean? It means that this user Aaron that you see on the side on the slide is a member of the intern team, but he's also a member of the temp team. Okay, because there's a path in the graph between those two. Now you might be wondering how we actually deal with this, everyone, right? Are we computing transit closure of the graph at runtime? Is this going to be fast? Well, the answer is that we don't. What we do instead, we define the semantics of CEDAR not on the entity hierarchy, which I'm showing to you as a way to visualize what's going on, but actually on the transitive closure of that graph. So the application that has the data is responsible for computing the transitive closure. The reason why we made that choice is twofold. First, for many applications, it actually makes sense to do this calculation on the fly. You do it on the fly, and you can have to do it. Okay, And then in Cedar, this in check becomes okay. For many applications, it doesn't make sense to do this in flat. It's too expensive. So what they're going to do is they're going to maintain the transistors incrementally or cache it and then pass it in and do stabilization this way. By defining semantics on the transit closure of this graph rather than the graph itself, we allow the application to make the decision that makes most sense for their data access patterns and for their performance. Okay? So this is actually what the input of the Cedar evaluator looks like. It is a finite map from entity references to the attributes of that entity. So Aaron doesn't have any attributes, if you enter record here, and to the ancestors of the entity. So Aaron has two ancestors, it's the inference and the entity. Now, this is how we do role-based access control. We do attribute-based access control. You can use these conditions, which are usually expressed over the attributes. If you've seen before, you can also express them over the hierarchy, nothing is anything. But to do classic attribute-based access control, this is how you would do it. This has operator here is testing for the presence of a field. So in Cedar records, you're allowed to have optional fields. You don't have null because nulls are bad, right? $1 million mistake, or I don't know, maybe I got the amount wrong, but there's the code, right? So we don't have nulls, we have option types, optional fields. You can test whether the field is present, and if it is present, you can perform an operation on it after you access it. This expression language is free of loops. It's free of side effects. It's a pure functional expression language. And the operators in the language are carefully chosen so that we can translate each and every policy to a decidable formula in SAP. Okay? So that's sort of the game that we're playing. We have to add enough operators on these data types, on the record, set, Boolean, strings, and so on for the language to be useful, but not so many that the language becomes analyzable. Okay? The operators are also chosen to enforce specific bounds on performance, so evaluation time, how long it actually takes to evaluate these both. Typically, if you're not using expensive set operations like testing for subset and whatnot, you're going to run in ORM time, where n is the size of your subset of data that's relevant to you. Otherwise, your stage time is still bounded. All right. Now, by combining hierarchies and attributes, you can encode relations in Cedar and therefore express relation-based access control. So what we actually do is for every relation that you want to define, we introduce an attribute. So if you want to define a reader's relation that goes from principals to resources and is transited via themes, you just define this reader's and editor's attribute, and then you rely on the hierarchy to test for the presence of these people inside the relation. Okay? We can express relation-based access control as well without needing a dedicated constructor. And the magic here that's happening is the fact that we're allowing users to store into references in the field as well. All right, so that is the language design. This is what feeder policies look like. This is what they mean. This is how we execute them. And now we're going to talk about the two aspects of Cedar that we really care about that are unique in the space of visualization languages, and that is the type safety and the analyzability aspect. But to check that a Cedar policy is doing the right thing, or at least mostly the right thing, we use a type checker, which we call the policy validator. What this policy validator does is it takes advantage of a policy like this and a schema for your application. So what is a schema? Well, a schema is a way to declare to Cedar what entity types are available in your application, what kind of attributes they have, what are the types of those attributes. So you can see here that we have this entity list type, and it has some attributes, right? It has readers, editors, owners, tasks, and whatnot. And the schema also tells the system what kind of hierarchy relationships are legal. Okay, so what a declaration for teams and users says is that users can roll up to teams. Okay, so they can be grouped into teams, but not into other users. That doesn't make any sense. So this is an upper bound of precedent. And teams can be grouped into other teams. So nested teams are allowed, nested users are not allowed. And that is the only kind of grouping that you see in this particular application. Another important aspect of the schema is the listing of all the actions that make sense in your application and that you are perfecting. Right. So what actions can you really perform on this resource? The action declaration can also have hierarchies. We're not showing that here, but the most important part is that it's effectively specifying a polymorphic method signature. Right. You give me the list of all principal types to which an action can apply, and the list of all resource types, and it can apply to the cross product filters. Okay. In this case, I'm keeping things simple. So the first action can be applied to principles of type user, and it can be applied to resources of type list. So I cannot apply this action to a resource of type application if it doesn't make sense, right? The action is only sensible to this particular resource and principal pair with particular aspects of the feature. Now, given these inputs, the feeder policy validator is going to perform at sensitive and flow sensitive type checks. So this is unusual, right? Most type checkers are not sensitive to either of these. The feeder is partially fast sensitive, but it is flow sensitive, and it's going to try to see whether your policy is safe according to this scheme. The first thing that it's going to do is going to look at this action declaration, and it's going to conclude that from this, well, if I look at my schema and the action is supposed to be get list, then there are only two possibilities. There's only one possibility for the principal type and one possibility for the resource type. Okay, I know for sure that they must be the user and the list. Next, because the resource is a list, I can tell that it has these two fields, readers and writers, and they're both of type P. And more importantly, both fields are required to be programmed. So I'm not showing here on the slide any example of an optional field, but if you had one, you would declare that in the schema by putting the question mark at the end of the field name. If you did that, the type checker would force you always to first check whether an optional attribute is present before accessing it. This is why the type system is flow sensitive. Right? You actually have to do the check and then see before you're able to access it. But in this case, the execution is pretty simple. You can type this resource.readers expression and the resource.editor expression as something of type P. Okay, so now we're ready to perform type checking on this in expression, and we do that by looking at the in declaration in the schema. Okay, so the schema says that principles may be in keys. So we know that on the right-hand side, we have a key. On the left-hand side, we know that we have a user for this type check as well. Okay. So if on the right-hand side, let's say this reader's field is referred to a string or something like that, this check is failed. It really makes sense to get it in. There are several other properties of the type checking in addition to the one that I described. So regular type safety with optional attributes, type safety with polymorphic actions, and we have implemented the type system twice in Lean and Rust, and in Lean, we've proven that it is fine. So if your policy passes validation and at runtime you evaluate it against inputs that conform to this schema, then the evaluation is guaranteed not to throw any type errors at runtime or any attribute missing errors and a bunch of other factors. Oh, type checking is nice. It's fast. It tells you things. But in some sense, it's a shallow analysis, right? A type checker can't tell you anything about the semantics of the code. And it's doing the right thing, it's giving too much access, not enough access. So for that, we turn to this quality analysis just based on SAT, and which is going to answer universal questions about the behavior of follow. Okay, what can happen on all possible inputs that are consistent with your application scheme. We've implemented a bunch of these, but the one that's easiest to explain and understand is the classic, which is policy equivalent. So suppose that I have a bunch of policies and I want to refactor them without changing too much. Have I done the right thing? So the analysis can answer a question like that. And here's a concrete example. Suppose that I have these two policies, again, for time to do. So the first one says that principals can perform the create and get own list action on the application. But if anybody who is in the intern can come and create the list. Okay, we don't want to bring things straight and creating it all over the place. Now imagine that you want to refactor these two policies and replace them with a single policy with no forbid. Okay, so here is an attempt to do that. You think I did it right? Are these things equivalent? It's hard to tell, right? I mean, the policy looks pretty sensible. The answer is they're not equivalent, and the analysis is going to come back and is going to give a concrete counterexample, a specific request, and a state of the entity store that's consistent with your schema on which the policies behave differently. So the one on the left-hand side is going to allow this because Aaron is an intern. He's actually allowed to perform the get on list action. The one on the right is not going to allow it because the policy says you can do anything unless you need. Okay, so we actually have to fix the one on the right in order to achieve the equivalent. And one way to do it is to make an exception for the state list action. And in that case, you're not going to come back and say, hey, these two policies that are now equivalent. The analysis works by symbolically compiling formulas, policies to logical formulas, and then using an SMP solver to check if the negation of the property that we care about is unsatisfactory. Okay, so this compilation process is type directed, and what comes out is a formula in a combination of decidable theories. So specifically, a small subset of the theory of strings, theory of finite sets, bit vectors, ADPs, and unitary functions. This compiler has to solve two unique challenges that come from the fact that these theater entities are arranged into a DAG. Okay, so we want these analyses to be solid and complete. So the completeness requirement is the hard one because we don't want any false positives. Somehow we have to convey to the solver that these things are arranged into a DAG. And as you will see shortly, the inputs to pseudo also finite, right? For this finite map from entities to attributes and things. So that's the core of the challenge of the compiler has solved. And I'm going to walk you through it with how we do this, what the challenges look like, and I'll give you some idea how we actually get this. All right. To do that, I'm going to use a concrete example, which is much simpler than policy equivalence, which reasons about multiple policies. So this simple example is trying to check this property that we want to check is this policy that I have here. Does it evaluate to false on all possible inputs that are consistent with the schema? That's the property we want to check. Does it actually evaluate to false? If it does, the check succeeds. If not, the solver is supposed to give you a concrete counterexample on which the policy evaluates the truth. So the formula we want to emit is precisely a formula and encoding of the semantics of those policies when the policy is. So how does this work? Well, the first thing that we're going to do is we need to construct a symbolic representation of the entity store and a symbolic representation of the request. To represent the entity store, we use the entity type declarations in the schema. So each entity type becomes its own ADT, abstract data type in the entity encoding, right? So the entity theme is represented by the type theme, and entities only have one property. Remember, they're just references. And the only property they have is their name. Okay, so that ADT gives us the name of that specific entity of type T. Now, for the ancestors and the attributes of the entity, we're going to represent those as uninterpreted functions from entity references to sets of ancestors of the right type as declared by the schema, and for attributes from entities to records of the right type as declared by the schema. Okay, so teams don't have any attributes, but they have some ancestors, and that's what the declaration looks like. The declaration for users looks similar, and the declaration for lists is a little bit more interesting because lists do have attributes. So what we do is we introduce an ADT that represents the attribute reference for list, and then we have list.attrs, which is this uninterpreted function, which maps list to list records. Okay, so here it is. It is a symbolic representation of all possible concrete entity stores that are consistent with this schema. Now, the next step is to use the relevant action declaration to formulate a symbolic representation of the request, which is going to represent the request. Okay, so in this case, the action is update path, and we're going to introduce two variables into our encoding. They're called constants in the SMP rules, but we're basically declaring two variables, one for the principal and one for the list. So using all these declarations, the compiler is now going to do a standard bottom-up traversal of this policy to produce an assertion, which is going to be true exactly when the policy evaluates the truth, if there is such a thing. Okay, so we're going to ask the SMP solver to find a binding for these variables and for these uninterpreted functions such that this assertion holds. To convince yourself that this thing is actually implementing the semantics, you can see that it's testing whether it gets the attributes of the resource, it gets the editor field of the attribute, and it's testing whether that's the member of the ancestors of the team. Okay, and the ancestor set here, remember, it's capturing the full transcript closure. So all of my ancestors, not just my parents. You can also see that the compiler is pretty clever and optimized, right? This is actually what it outputs, even though I manually choose to make the names prettier, like none of the names that you see encoding makes sense. But this formula is actually what it outputs, okay? You can see that it's smart enough to decide that this constraint action is equal to action update task is always true in the schema, so it's not going to emit anything related to that. It's only going to emit this minimal thing that's necessary for this policy value to true. All right, a quick question. Any takers? Is this formula satisfiable? Is it stacked? Can this policy value the truth? Can you imagine anything in which it does? Well, my example wouldn't work if it wasn't satisfiable. So it is. And here is the model that the SET solver produces. Okay. So this model is saying that if you have this principal called Alice and you have this list called 1, 2, 3, Alice is allowed to by this policy to access this list if the hierarchy and the attributes are set up in this way as shown in this model. Now, this model does satisfy our constraint, right? We're assuming that the SMP solver is correct. But it doesn't actually correspond to any valid feeder input. To see why that's the case, you have to remember that the hierarchy in feeder is supposed to be a DAG. Now, if it's a DAG, then this ancestor relation that we're constructing using these uninterpreted functions better be a cyclic and transitive, right? Its transitive closure better be a cyclic and transitive. But it's actually neither. Nothing is preventing the SMP solver in the constraint that I've given you from making it cyclic and not transitive. So to see that it's cyclic, you can see that the ancestor relation of teams says that every team is mapped to this particular set of ancestors. Okay, so interns and teams, including interns. Therefore, there's a cycle in there. Okay, bad. We don't want that. The second problem is that this relation, as the SMP solver found it, is also not transitive. Okay, So it says that every user is mapped to the intern speed. But if you're mapped to the intern speed and the intern team also mapped to the speed, to these temp teams, users should also be mapped to the temp team. So we violated both constraints. It's the first speed and transitivity. So the question that we have to solve then is, well, how do we fix this problem while we're inside of it, right? You can easily imagine how you could generate a significant transparency constraint on these functions using quantifiers, right? Super easy, but that takes us out of the decidable lane. We want to stay decidable. How do we do it? Well, the insight is we're going to rely on the fact that theater policies do not have loops. Because they don't have loops, the set of entities that are acceptable by evaluating any policy on any input is finite. In fact, we can statically over approximate that set. So if we take those sequential transitivity constraints and ground them on that set, we're going to constrain the solver to give us well-formed shapes of the hierarchy, at least for those inputs, at least for those entities that are reachable by the execution. To be more concrete, we call this approximation to the footprint of the policy, and it is computed as every sub-expression of the policy that is a type entity and that may have an agent. So according to our schema and this policy, there are only two expressions that represent these and such entities in the footprint within this policy. So anything that's reachable from the principal and the expression resource of editors, which you may remember, is of type P. Once we have the footprint, we can generate the acyclicity constraints on it and the transitivity constraints on it. For acyclicity, the only one that matters is resource of editors, because teams may be wrapped into other teams. So here's the constraint that we emit, okay? And it does what you think it should do. It's basically saying that if you take the editors of the resource, well, it better be the case that that team is not a member of the ancestors of the editors of the resource. Okay, so we're encoding acyclicity on this particular expression that may occur in this policy. For transitivity, the constraint looks a bit more complicated, but it also does what you think it should be doing. It's basically saying that if the editor's team is a member of the ancestors of the principal, then it better be the case that all the ancestors of the editors are also the ancestors of the principal. So that gives you this. So when I add these two constraints to the solver, policy still satisfiable, right? And I get something that looks better. Okay. So here is what the solver says the principal is, and here is what the resource of editors evaluates under this model. And you can see up there that we preserve transitivity, at least for the things on the footprint, and we preserve explicitly on the things in the footprint. But we still have a problem, right? There are two problems actually. So one is that we don't preserve these constraints on things that are outside of the footprint, right? I mean, nothing forces the solver to make this temp team recyclable because we didn't emit a constraint that says that, okay? And in fact, it does have a cycle there. That's problem number one. Things that are outside of the footprint are still ill-formed. And problem number two is that my symbolic representation of the theater entity store is infinite. I'm using uninterpreted functions, which are infinite maps that are total over the domain, to represent the ancestors and the attributes. How do I extract a well-formed finite input from a partially well-formed infinite SMT? Okay, so that's the final challenge that we have to solve. And the intuition is basically that there are two facts that we can explore. The first fact is to know that if your formula is quantifier free, which ours is, then these function models emitted by the SMT solver are going to have a particular shape. They're not going to be arbitrary functions. In fact, they're going to be implementing a lookup table with a default value. So you're going to have this is enough expression, which is going to tell you the values for specific points in the domain for which it matters. And then everything else is going to default to the value in the final output. Okay, so this is what those models look like. If you look at tables related to that. That means that even though the domain of the function needs infinite, the range is finite. And we can exploit that fact to extract a finite context. So that's insight number one. Insight number two is for every entity outside of the footprint, we can completely ignore the ancestor set returned by the solver and replace it with the empty set. And we will still satisfy those frequency constraints on everything. So using these two facts, what our extraction algorithm returns here as a counterexample for this model is what we would expect. So you can see that this policy varies between this input. So we have our user Alice, and she's in the feed meters and 10, and she's allowed to access this list 1, 2, 3, basically saying that alphabetically, if the policy varies default from our input is violated, with a complete case. Now, we have implemented all of this in a symbolic compilation, generation of these hierarchy constraints and counterexample extraction, and we have proved that the entire process is found by complete, meaning a policy analysis that is built out of these components is guaranteed to have no false negatives. If it comes back and it says property hold, it really does, and it's going to have no false positive. So it comes back with a counterexample, it's going to be a real well-formed counterexample to your problem. All right. That brings us to the final part of the talk, where I'm going to briefly tell you about how well speedup performs and how we actually did all of this stuff that I've been talking about in the US. So speedup itself, the production engine, the thing that you click down to download and put into your PC, is implemented in Rust. It takes the input, gets expressed and see their policies, evaluates them, and returns allow organized plus resource diagnostics. The fact you get something called the request with allow order. This evaluation is very fast. A typical request takes less than 10 microseconds. And this is 30 to 80 times faster than other authorization systems, which are based on languages that are richer, right? So in some cases, they trade expressiveness for performance, and in some cases, they have a more complicated data model, which will be affected. Now, Rust gives us memory state, but in order to actually check that implementation is correct, we use differential random testing against our lean code. Okay, so every component of CEDAR that I talked about today, the evaluator, the authorizer, the type checker, the symbolic compiler, everything is implemented in Lean, and those, as well as Rust, and those implementations, the Lean ones, are executable, which means that you can use them as step oracles for the first one Rust code. In the case of the authorization in particular, we're going to generate millions of random inputs, requests, and the data policies. We feed them to go the specification and implementation. We get the result back and we compare them. If they agree, well, you have one piece of evidence that the implementation is correct. If they disagree, we found a bug. Okay. Now, the Lean specification is designed to be provable. Okay, it's designed to be executable. It's designed to be readable and small. So all of the components of CEDAR, everything I talked about, it's less than, it's about 5,000 lines of code. Okay, so this is basically formalizing the entire CEDAR language and a substantial subset of SNC. Right, it's 5,000 lines of code. We have much more Rust code. Right, it's like about 80 code. Now, in addition to being a reference to the implementation that's readable, Lean, because Lean is a pure improvement, we also use it to actually formally verify all the properties that I talked about. So, forbid, transmit, counter the type checker, counter the compiler, everything. And all of that amounts to about 39,000 lines of communication. But it's actually not bad, right? Compared to how much stuff goes with it. So not too bad. And then the question, of course, is, well, we do a lot of work. We implement everything twice. We prove what the thing is working. Did we find anything interesting? And the answer is yes. So these stats are a bit out of date. We actually have done, we have found more bugs in this, but At least 26 bugs were found by DRT between the implementation and the specification, and at least 6 bugs were found in the design stage to fail proofs. So we would write a model, we would think it has a nice property, we would try to prove it, it would fail, figure out it might fail, go fix it, and redo the proof before we actually get it into implementation with production. So that brings us to the end of my talk. Thank you very much for your attention. I'll be happy to take any questions now. I think you can end here. Yeah.
Thanks so much. And I'll run back and get questions.
Thank you for a wonderful talk. I was thinking when you were talking about the symbolic compilation, you never said the words model checking, but it did seem to have a whole lot in common with model checking. And I was wondering if you could tell us a little bit more about that relationship. For example, is this essentially encoding an entire model checker? Like could you, for example, potentially win the software model checking competition with this, or use it to improve those model checking algorithms? What's the relationship there? Because it looks like you've done a lot in that sphere that would be highly related.
So the algorithm that we built is very specific. In that sense, it's not going to generalize to other languages. But the approach is actually generic. So what this is doing is implementing a hybrid of symbolic execution and bounded model checking in order to emit this formula, which is going to be sound and complete procedure because it has no loops, right? If you had loops, then ours wouldn't be, because you would have to bound the number of steps that you're encoding. But in a loop free, you're going to end up with something that's sound and complete. The other nice thing that we've done is develop this proof method for actually showing standard the completeness of these reduction algorithms. And there is a trick that you can use to make the proof much easier than you would have in a normal compiler correctness proof that does by simulations and stuff. So yes, the concrete algorithm is very specific for students, but the ideas and the approach will generalize to other methods.
Okay, thank you, Emina, for the very nice talk. So I have a question. So I was thinking, for a real application when someone is writing a policy moving header, and it may also change over time. So the rules become, complicated, and they can add user, they can have a rule, and you have again exception around. So maybe they can become very, very big. So there is a way to take a policy and produce automatically a thematically equivalent one, which is simpler. Or have you thought about doing something like that?
Yeah, that's a good question. So there would be some of the classic synthesis problems. Like we have the current test, which does something that we like, but it's really complicated. We need to use a simple one. We haven't tried it. Of course, I have to mention the story, guys, in LLM. So people have tried doing this with LLM. And the nice thing about having a verifier is that it can actually check that this thing is information. It turned out to be pretty good. Like they will get it right close to right most of the time, and the verifier says yes or no. And we have also had some people that had some success at putting this into a vision, right? So when an LM comes up with a reflexive policy, if it's wrong, you can feed it down constantly. And then it will try to come back together and,
If you have enough data example, I guess that.
Yeah, there are lots of good examples of that.
So, yeah, so thank you.
Thanks for your talk. I was curious about the differential testing. So you say you do random differential testing. Do you do any directed inputs? Yeah, I mean, because of course there'd be a lot of invalid inputs.
Yeah. We do coverage guided random directed testing. So a lot of the Rust code that we wrote has to do with intelligent input generation. Because if you really randomly generate inputs, you're not going to get anything interesting, right? Because these inputs have to be very intricately interrelated, right? So the request better be referring to some entities that are defined in this randomly generated entity store, and the policies better be referring again to entities that are in there. Otherwise, you're going to get random errors. So it is. We have custom generators, and it's coverage guided to maximize the coverage for the rough.
Thank you, Amina, for the very interesting framework. So I have two questions. The first one is, can you detect a kind of orphan mistake, orphan resource, like maybe because of the set of policies, there is a document or a resource or something that matches some constraints and that would be not accessible by anyone. So that's a can you detect it? And the second is, how explicit is the language? Can you, for example, add a little bit of like dynamicity, or if I get access, then the other will not have access, like for a moment, and then can this be captured by the framework, or it has to be programmed outside of it?
Yeah. They're both good questions. So to answer the first one, can we detect if a resource is not accessible for everyone? If you are able to express that question as, let's say, a pseudo forbid policy, then we can check whether that forbid policy intersects with any of the other policies using analysis that they tell you that it's acceptable. So we can definitely do that. For the second question, the language is not dynamic at all. It's purely functional, one shot. But people do use it to protect in these authorization workflows by keeping the state outside of SQL. So you can have these complicated workflows that do things like, okay, well, you are asking to perform this action, which means to sell X shares of this stock at this point. But you're only allowed to perform that action if you have gotten approval to share, to sell as much X shares. So all of that, you're going to need two authorizations from the authorization. You're going to keep all of that space out. In that case, I think going back to the model checking question, you could imagine doing a model checking with a combination of the Symposium compilation that we have that's going to check the privilege information, right? So in two steps of me adding another policy, can I get to a state in which I now have access to the information?
Thank you, Mina. This is very exciting work. I'm curious about the engineering process. Let's say that there is a modification to the language, so you have to redo the proofs. So who's going to do that? Doing engineering is the software engineers or is field group? So who's working on maintaining those proofs? And the second part of the question is, are you planning to have maybe automated extraction of the code from the specification in Lean? Because you have an algorithm that is executable. You can think about extracting the code directly from that. Thank you.
Yeah, good. Both of them are good questions. So the proofs are maintained by the applied scientists in this team. So there are engineers on the team, and there's a core part of the team, which is 6 scientists, including me, and we maintain the proofs. Now, a lot of the effort that went into developing these proofs went into ensuring that the proofs are maintainable and that you're going to be able to evolve them and add new language features without expending so much effort. So to give you an example, I built a symbolic compiler and all the page that was about 20,000 lines of code, right? I built it and I froze it last year. And since last year, 3 more features have been added to the language. And the hardest one to add, which was not done by me, because somebody else actually modified my proofs, and they didn't know Lean. So they had to learn my entire code base and learn Lean, and they were able to do it in 8 days. And this was a substantial feature. They actually added an including of bake time and all of those nasty operations to the compiler and so a lot of the effort that we put in goes into making sure that the proofs are stable and that they're maintainable. And the core science, applied science, is input. Now, to the second question, we can extract the code. It's a good one. We haven't tried it. I think we should at some point. The main issue is being able to extract code from the lean model that is understandable by humans. So the lean compiler itself is extremely efficient. In fact, all of the lean code that we build runs as fast as the Rust code. So you might be asking yourself, well, why are you using the lean code, right? Well, because it generates features. And people are uncomfortable with it. It's completely if you cannot understand it, people want to be able to read the code that they're running and that's open to. So that's one hurdle. So if there was a way to extract idiomatic, human readable code from the learning models, I think that would be one. And we haven't looked at it.
I know there are more questions, but we are already a little past our cutoff time. So if you have more questions, Amina will be around at least for the break, hopefully for the rest of the day, hopefully for the lineup. Thank you so much for your talk. Let's give a round of applause. And we have a break for a half an hour. There are snacks and coffee and tea in the back. We'll start back at 10:30. Thank you.
Okay, everybody, let's get started for the next session. So the next talk will be given by Mikael Shetty. It's on automata size reduction by procedure finding. And he is now a PhD student at Harvard University. And this work has been done at Bruno. Right? So thank you.
Okay, thank you for the introduction. Yeah, as you can see, we have with Luca Tori, we've been working on this project. We have pretty interesting affiliation to two of the universities, but now we mainly are working on Aalborg University in Denmark. So today I will talk about the new automata reduction approach that uses repetitive subtractors in automata to reduce their size by replacing these repetitive subtractors by one procedure. So what is it going to be about? First, I'll talk about some motivation behind this research. Then we will have to go through some definitions of automaton, where we use the procedure, how to implement it in the automaton. And then I'll talk about how to find these repetitive substructures in the automata, how to replace them with the procedure, and I will show some optimizations to this algorithm. And at the end, we will finally look on some beautiful graphs and papers with the results. So why do we need to minimize automata? I think that this question is really basic, and everybody knows the answer, that the size of the automata is a real problem. But we've been mainly driven by the fact that we want our automata to be implemented in FPGAs for network scanning. We want to scan high-speed networks with speeds up more than 10 gigabits per second. So we need automata to be as small as possible in order to be able to efficiently implement them in FPGAs. And why not to just use existing techniques that are based on language equivalencies? They can be approximated using simulation or dissimulation. Well, the fact is this automaton on the right, where you can see that it represents a regular expression consisting of two parts, where the first part matches the XML HTTP request, and the second part, the file protocol. And these three parts can swap the place. But in standard NFA, you don't have any other choice to represent this than just by these two different parts. And you can see that there is a lot of redundancy. You can see that we have 3 times HTTP request here and the file protocol. So why not to represent it only once? So we took an inspiration from programs where you exactly represent similar blocks of code only with one procedure, one function. And then you use call stack, remember from where you enter the procedure and where to return. So yeah, with this idea, we went for the reduction, and now we need to go through some definitions to be on the same note when talking about the automata procedures. So we took the standard definition of NFAs, where you can see some example of the automata on the right, and we extended it with the register. This gives us a register alphabet gamma, and we introduced two additional symbols that are not part of this gamma alphabet. So the bottom that represents default register value, and then the star, which we call wildcard. And this is an essential symbol for our transitions, where you don't care about the value of the register, just take the transition, don't change the register value. And this brings us to 5 types of transitions we can have here. We can have call transitions that store some symbol alpha on the register, or return that tests if the register value is alpha, and if so, then take this transition and empty the register, and so on. We can swap the register values, just test if there's alpha, so then proceed and keep the alpha on the register. And then the most important transition, this is the type of transition that really brings us the savings, is this common transition who uses the wildcard to create a shortcut for more transitions, more guard transitions that would need to test for, let's say, 10 different register values. Then we can just shrink it to one transition and say, oh, don't care about the register value, just take this transition. So you can see that here on the bottom, we have the exact language of the upper NFA, where we figure out that, hey, we have here 2 similar subparts. The orange one that goes over transitions AA, and the bottom one that also goes over transitions AA. Of course, there are some unique transitions that belongs only to one of those substructures, but we can deal with it by, if we merge them into one procedure, then we can only by testing the register value to check only, oh, this transition can be taken only if we enter this procedure from, if we take this procedure and it represents the original substructure, the orange one. So this is how it works. And you can see that the common transitions with the wildcard are those ones that represent that there is a transition in both of these substructures. And it's the most important thing you have to take with the slide. So now how to search for these similar substructures. So to do this, we used something called self-product, which is basically a product of automaton with itself. And you can see that we have to, of course, make all states initial and final. And here on the bottom, you can see self-product, part of the self-product of the automaton above. And it tells us what are the possible similarities, language similarities in the original automaton. And now the question is how to select the best subproduct of this graph that will tell us which 2 states to merge and basically how to create the procedure. Well, we find out that we need 2 constraints. The first one is really basic, that we want to have the most savings possible. We want to find the subgraph in the self-product that represents the most redundant transitions. And we also figure out that we don't want to repeat states. So, for example, we don't want to take this subgraph where we have Q1, Q2, and then you want to merge Q1 with Q4 and then Q1 with Q6. So just basically some constraint we figure out that we need that. So this brings us to only one solution in this case, and it is to merge states Q1 with Q2 and Q3 with Q4 and Q5 with Q6. So now we know how to search for the best candidates for the procedure, and it also tells us which 2 states to merge. So now with this knowledge, we can get back to the motivation example. where we have this beautiful automaton, and somebody already told us that we will have two procedures, one for the XML HTTP request and one for the file protocol. And to know in what original substructure we are, we assign a unique symbol to each subtraction. This unique symbol on the register will tell us where we are. So by doing so, we can map renditions for the left path in this automaton, and just remember on the register that we entered the orange substructure, then we exit the orange and enter the red one, and so on. And we can do the same thing for the right path. So now we can see that we eliminate the redundancy in the automaton structure. And you can maybe see, maybe not at this moment, but we don't need so many unique symbols to distinguish between those structures. We figure out that we only need to safely distinguish those symbols that can meet at the register at some state. So we come up with this relation that is an equivalence relation if procedures have strict tree-like structure, which tells us that for this example, we for this example, you can see that we need to distinguish between the orange and the green symbols in order to know where to go. So you can use this equivalence relation to create equivalence classes, and it will tell you how many states, how many register values you need. Because you need at least such an amount of register values as is the cardinality of the greatest equivalent class. So this brings us to this optimization when we at the end need only two register values to distinguish if we first enter the HTTP request or first we enter the file protocol procedure. And now just before the results, we should talk about how to measure the reduction. Because for transitions, it's pretty obvious. Let's compare the transition before and after the reduction. But for states, it's something different. We have to be careful about how we do it, because I think that all of you can easily imagine how to create only one state automaton where all the logic of states is put on the register. The register now just remembers in what state it is. So there's no reduction at all, but we have only one state. You have to incorporate the number of registers and both you use in order to tell the reduction. So this is what we are doing. We take the sum of the states and use the register symbols and compare it to the original number of states. So now let's go to the results. So now I should tell that we are using our approach as an additional step to existing techniques. So first we apply state merging and transition pruning. We obtain some auxiliary automaton, and then we apply our techniques. And we compare the results of our techniques to those auxiliary intermediate automata. So here on these two graphs, on the left graph, you can see distribution of reduction in the number of states over automata from parametric regular expressions that contain cycles. And you can see that we in most of the cases hit the reduction about 50% in the number of states and 50% in the number of transitions. So we achieve additional reduction to existing techniques that was about 50%. So now have to do some more interesting benchmarks. Those were in regular expressions for validation of email addresses. And here you can see that we still managed to achieve some interesting reduction. We achieved about 40% reduction in the number of states and almost 30% reduction in the number of transitions, which is really something I would say if we had already achieve, let's say, not the minimum size, but we reduced it as was possible by existing techniques, and then we come up with a technique that was able to reduce it by another interesting person. So now back to the network filtering. We took about 3,500 of regular expressions from Snort, which is a tool for network filtering. And we divide it into 7 families of the rules, and then perform a union of all regular expression in each family. And this led us to 7 big automata. So you can see that the automata reached almost close to the 1,000 of states, and in some cases, the automaton has had almost 60,000 transitions. So after performing standard reductions using tool RabbitReduce, which utilized state merging and transition pruning, we achieved they achieved not bad reduction. It was in some cases about 50%. And then we can look maybe on the most important and interesting results. Let's say MySQL, where we, after additional application of our approach, we were able to reduce the number of states by an additional 30% and the number of transitions by 50%. And you can also see that to do so, we used originally used 18 unique register values, but after the optimization using the meet equivalence relation I showed, we are able to reduce this number just to 5 unique register symbol. Another interesting result is this specific thread, where we reduce the number of transition by additionally nice 60% and the number of transitions by 44%. And this is really something if you consider that you want to implement this in FPGA. Now you can save approximately half of the lookup tables. So this is very interesting. And just to mention, in the last row, telnet rules, it originally used 82 unique register values, which is a lot. And you can see that by using this optimization, using the meet equivalence relation, we are able to reduce it to 4, which shows the importance of this optimization, because otherwise the reduction would be just some small percent. And this is nice to think of it like that we achieved something very interesting here. So, and this brings me to the end of the presentation, where I would like to share what we would like to do and what we dream about in the future. And one of the things is that we want to improve or extend existing algorithms working with automata in order to be able to leverage the procedures. Because of course we can make automata smaller, but it would be nice to use these procedures to fasten, make faster, for example, equivalence checking, or to use it in model checking. And of course, there's the implementation of these automata in FPGA. We're already working on it, and the results are pretty nice. Also, you saw that we're using this self-product of the automaton, which is not very optimal thing. So we would like to come up with something more efficient. Also, 1 register is nice, but we're also thinking about using some limited step. And if we can detect procedures, then we would like also try to detect cycles in the automata, which would not only reduce its size, but also improve the readability and human understandability of the automata. So yeah, that's all. my side. And thank you for your attention. And if you have any questions, I'll be happy to answer them.
Thank you.
So any questions?
Thank you for a very nice talk. I had, I guess, two questions. One was when comparing how much you reduced resources, what were you comparing against? And I guess kind of a related question is, as you talked about FPGAs, FPGA tools are typically pretty good about if you like make a state machine, give it to the tools, they do a lot of optimization. So if you compare it against like how well FPGA tools can already optimize finite state machines and such. Thank you.
Yeah, okay. So at this point, we just compared the number of states and precision in NFA and our automaton with procedures. And now we're trying to do this for FPGA as well, where we compare an implementation of NFAs with on-the-fly determinization in FPGAs, and then our single finite register automaton done in the same way. And there we compare the number of lookup tables for both of these representations.
There was another question.
I was curious. I mean, this might be a terrible idea, but did you think about generalizing the size of the, like doing a larger register, so having a stack and having some fixed size?
Yeah, we were thinking about increasing the depth because now we can't have nested procedures. So yeah, it's one of the directions of further research to try to have stack with some bigger depth or more registers or complicated registers with some register operations like increasing counter or something like that. Yeah, we're thinking about it.
Other questions? I'm very interested in your application. And do you use that? Do you use it in offline or in an online fashion?
Like we would like to use it in online fashion.
Are you anywhere near real time capable with that? Or
Excuse me?
are you anywhere near real time capable with it? With the reduction, does it make it
Like
possible for you?
No, the reduction is not able to do it in real time. We would like to first spend some time on the reducing this automata, then implement it in hardware, and then it can work that way. So we don't consider the cost of the reduction because it's something you in our part it's something that you can spend some time on because at the end you'll be awarded with some nice appreciation.
Thank you. Thank you. If there are no more questions, let's thank the speaker again. And maybe the second speaker could come up. We are doing fine time-wise. So the second speaker is Matthias Brizio. He's a PhD student at India Software Institute in Spain. And he's going to talk about mode-based reactive synthesis. Slides already look beautiful. And the floor is yours. Thank you.
Morning, everyone. I'm Matthias, and Malway Synthesis. Let's start by defining what a rapid system is. The cognitive system are continuous interaction with their environment. Think about listener, writer. They are continuously replying to time they talk. In the environment, for example, the air conditioner takes the temperature in their ultimate states, and then producing some outputs that can eventually modify the environment again, and the environment can send new requests to the system and the response and so on. Okay, so air conditioner can it on or it off, modifying that way the temperature. As we can see here, it's an input and output relationship between the inputs and outputs, and it's an infinite relationship because this kind of systems lives forever. Okay, how can we formalize, how can we capture this relationship between those and inputs? This is captured in requirement engineering using domain properties and goals. Domain properties are descriptive, the statement about the environment, how it behaves, what are its variants, and the goals, as the name suggests, are those goals that the system has to complain, putting in interaction with the environment. So this relationship is captured formally using different temporal languages. The most common one is LTL, linear temporal logic. And well, once we capture these goals and assumptions about the environment, we have a kind of interesting problem that is the rapid synthesis that try to get a controller that putting in interaction with the environment satisfy every single goal of our system. It's problem try to construct that controller automatically. If we can do that, we said that specification is replicable. If we cannot do that, we said the specification is unrealizable. But it seems straightforward, right? But we have a big problem here. It's exponential complete, so it's computationally so hard. And so the key question here is how can we efficiently obtain a controller from a formal specification? And that question triggers an interesting relationship between two different communities. One is requirement engineering community, and the other is rapid frequency one or formal method one. From one side, we have with rapid synthesis community that try for a formal specification that a controller that satisfy every single goal on it. And on the other hand, we had a rapid or requirement engineering community that try to specify in a human readable way those systems. We have here an example of SCR language. We have here another from NASA PRET. And here a comparison between different requirement engineering languages using in industry. And as we can see, all these kind of languages share one thing. They are talk about modes. And if you think about it, it makes sense because it's the way we as human beings think about specifying system. Some machine is in state on, then have to do something.
Then when something happens or some internal state change, the machine will be in state, I don't know, idle, and then we will be doing something else. So it's a natural way of thinking, that kind of basement. So why don't we meet those different community in one data block? That's what we try to do in this work. Before I continue, I would like to mention different running of LTL that I've used, that I commonly use in Justice 5 systems. Year one and safety are more common because they allow efficient synthesis. But in this work, we will focus on a more compact fragment that is called Net0 that allow us to specify different safety properties, and the fragment has the following form. We have the initialization part, where as the name suggests, is the initialization of the environment and system, where E is for the environment and S system. And we, on the other hand, we have the common adjoint guarantee part that is present in every rapid synthesis problem. But this part, the assumed guarantee, is writing in LTL heads. Also, the name suggests it's an fragment of LTL that only contains the nets operator. So we were talking about modes, but what I think, how can we formulate them? So there's a typo in the first line. A mode is basically a predicate, a state predicate over the system variables we have. And to be able to use kind of modes to decompose a specification, we need to have different conditions. The first one is the that by every mode it's showing that is only one is active at a time, and the other one is a complete. That is all the modes model the whole behavior of the system. For example, if we have two modes for on and off, or not on because off is just a string of sugar, is a valid set of modes because it is joined and it's complete. But we create another group of modes, we do have on and off and idle. It's not a valid one because it's joined, but not complete. So how can we use these definitions to decompose that case? To do that, let me introduce a simple example. That is a counter machine that receives sticks from the environment and counts until 20, and then start to count again. A stick machine will look like this, a very simple one. Here we have environment variables and the system one. Nevertheless, this specification is of first. This same machine is straightforward. Any practice synthesis of the state of the art can synthesize this controller because the Q relationship between the variables. So, what if we group the effect in different modes? For example, having a mode from count to 1 to 2, another from 3 to 4, another from 5 to 6, to 20, or maybe grouping group of 4, and so on. And then synthesize them, and after that, compose in a specification that, in a simple machine that satisfies the original specification. This machine, if we write it in LTL, it will look like this. The function, we have the other hands the guarantees, and if we have the specification as we saw in the state machine, we will so here is a mutually predicate that operates over the counter variable. We will obtain something like this. For example, the first is a mode from 0 to 1, the other is from 0 to 3, so on. And in this case, the mutual predicate is produced instead of having one variable. Now we have only two, but here's wrong. because we can't simply text the decompose specification like this. It goes against every format stuff. So why is that? Because if we are, our previous example, if we are in the mode 1, for example, in counter 2, and then with the system receive no respect from the environment, it has to transition to a new mode, okay, mode 2. But you need to inform the new mode that has to start 3, not 4, for example. Mode, for example, from 3 to 6, we need to inform that 3 is not 6, not 5, or not 4. So how can we do that? How can we calculate this condition? And remember the previous specification. If we look at it, we saw that this part doesn't go down to mode because we said that the mode for this is count of 0 or count of 1. So count of 2 it doesn't go down to 1. So we need to jump decision to another mode when the trigger predicate false. But we need to remember and pass into the new mode the state of the machine before jump. And this is called pending obligations. How can we capture these pending obligations? Basically, we inspect inside every single next formula and replace them with a new variable that handles their needs. Case, and the bundle also introduced two new guarantees, down and jump, that indicates that mode has finished its partial work and transition to another one by using down and then jump respectively. And so we rewrite the requirement in this way. We have here the S sub-3 that is counted or reset, and that is a pending obligation that to be captured by the next mode. So pending obligations are nice because they are all the obligation of mode ask for every single successor. I don't know who, but I ask for any one of my successors to complete something. And on the other hand, cumulative obligations are all those obligations that my predecessors asked me to complain at a certain point in the time. As a straightforward way to compute them would be just a union of all the pending obligations from the predecessors, but it's not a correct way to do that because take this example. Here is just an interleaving between two modes, and after two steps of time, the system has to satisfy P. We have P pending obligations, then the cumulative obligation using the definition that it's above the light. We obtain this, but if you take a look inside the trace of the system, we start in M0, and we have pending next P. Then we move to M1, pending next P that's here in the cumulative obligation, so that's right. Then we go back to M0, and we should satisfy P. But if we take a look, it's not present in our cumulative obligation. So if that union of pending obligation is not correct. So it's this. We introduce a algorithm that basically search for every next formula inside the cumulative obligation set, then get the derivatives from every single formula, and then pass them to the successors until at this point is reached. In this case, it's simple because it's just one net fee and the derivative is fee. But if we would have net fee, the derivatives will be net fee and then track to the successor. So in this case, using that definition, we have P in the cumulative obligation set, and the the mode 0 can satisfy P. So this, after computing this initial, that cumulative obligation, it's important to have intersect all of them, because different mode can jump to another, to the same successor, and ask him to satisfy different conditions. So that behavior is captured by initial conditions, that it's basically a conjunction between all the subset of cumulative obligations we have. In the previous case, the previous application, if we use the definition above, we obtain that it's all the initial condition for M1 and all the initial possible condition for M0. And we take a look again to the trace, we observe that it's valid because M0 have to satisfy at any time of the trace, no matter what, have to satisfy itself, of course, and P. And M1 at any time of the trace have to satisfy himself and next P. So after defining initial conditions, pending obligations, and cumulative obligations, how can we use all of these things to decompose? That is done by this algorithm. I'm not going to go further in details because it's out of its scope of paper. But if you have any questions, you can ask me anytime. But the most important lines here are 14 and 15, because they take the initial condition we compute to allow a mode, to indicate a mode that when it's able to jump to another successor. That is me, successor of a mode, I am able to continue the game. So you are safe to jump. That is taken, that is done. Take one initial condition from our set and then checking by using stat if the condition is satisfied by the successor. In that case, you can jump. As we can see, this algorithm heavily depends on the initial condition to make a transition to a new mode. So how can we search and find them efficiently? And we do that by using search-based technique. As any search-based technique, we have to define what is specs, what is our pool of individuals. In this case, take into account we have three modes, and this is the relationship between M0 and jump to M1, M1 to M2, and M2 goes back to M0. And assume for this example that every mode, after computing the initial conditions, have only 5 possible candidates. So our universe of individuals will be a mode instant graph that is basically a Cartesian product between the transitions between modes and between the initial conditions. For this case, it would look like this. Take into account that the first and the last line is the same of 0. That's probability. And what we do here is try to find a subgraph in which every single node, the mode is realizable. And that graph is called realizability group. So for this example, we start with the first node, with the first candidate, and then we try to get it realizable or not, assuming that all the possible successors, all the successors have all possible initial conditions active. So we check realizable or not. This case is realizable, so we go to the successor and try to get if realizable or not, having all the candidates successors activate. In this case, if the first is realizable, the second is not, the third not, And we can discard them because we have all the successors activated. So if a node is unrealizable, having all the possible jump activated, if we remove at least one, it will be more unrealizable than before. So that's why we can safely remove from the graph. We check, the last one is also removed. So after this iteration, we go back to the first one. We thought that we have to recheck its realizability because three modes of the successor have been removed. So we check in this case realizable, and then go to the second one, and this process is repeated until each point is reached. So the whole technique is like this. We receive a assumed guarantee specification writing in GH0. We receive a set of mode that is predicates for those variables, a mode graph that is totally optional and that defines the transitions between one mode and another. We compute the operations, initials, then we create the MIG. We obtain the projections, the reductions using the other algorithm I told you, and then we start a Bloom process to find a realizability graph. So to evaluate this, we do experimental and use it around with a question. We can effectively compute initial conditions if we can improve the synthesis time from state-of-the-art tools, and if we can complement other decomposition tools out there. To answer Richard's question 3, we compare our tool with the state-of-the-art decomposition tools. Benchmark with a specification benchmark to the soda tools and our tool, and then we pass it to a stretch to see if we can the specification is realizable or not. In this case, any of the soda tools out there can decompose the specification in benchmark, and that is because this kind of tool focus on the system variables to make a decomposition. They look in requirements which share some kind of variable, then group them in on direct articulated graph and produce a decomposition. And in a specification that it counters, all the system variables are related, so no decomposition is possible. It's basically the monolithic. After that, to answer Richard's question in 2 and 1, we take the same benchmark and pass it directly to Fritz to see realizable or not, and we pass it to our tool to see if we match the results with estimates. And as a side note, it's important to know that this technique is sound and it's semi-complete. That is only complete under the condition. That's why the realizable results are consistent with the traits. And in the case of unrealizable, we adapt the specification to the condition we use that is called mode-based determinism. It's basically to say that every mode is, every successor is only determined by the actual state of the system. So under that condition, we check the unrealizable cases and also find initial conditions for everyone. In case of unrealizable, we can find it because it's unrealizable, but improve the synthesis time as well. And we reduce the time over 8 years. And to sum it up, as a future work, we are trying to make the technique complete and expand it to a more larger fragment of LTO. And we also are exploring using genetic algorithms and LLMs to try to get a mode from a specification. So given a specification, not writing using modes, try to derivate one that is right in mode, so this techniques can be used. Thank you for your time.
Thank you. Is there any question?
Thank you, Mata. Very nice talk. I have two questions related to controls, obviously, because when you started your presentation, you talked about controller synthesis, right? So the first question is there a description of what exactly was specified in LCL and what was the controller? Maybe I missed that. And the second question is, how does it relate to, there's a large body of work in controls literature, for example, done by Tabuada, Papa, where they actually have hybrid system, because I did not see, maybe I missed it, the plant description anyway. But seems like there are examples for cruise, maybe it's cruise control, I don't know.
I think I missed the question. The second one.
The second one? Yeah.
Yeah.
So there is a lot of work on synthesis of controllers.
Yeah.
When you have an NTL spec, but when you're doing controller synthesis, there is a description of the plant, which is the state, the space. of model,
Ah,
right? Yeah, but I don't think I saw that because maybe thermostat is the only example there.
Yeah, those explorers say that is some work in Gagas, they focus more in planet robots, that it's other kind of sophistication that is in other fragment that we use. So that's why we cannot compare with them, but we also try to fund this fragment to be able to include them into this tool.
The questions? Shouldn't walk backwards. Okay. So I would like to know, you mentioned up there that your future work includes making the technique complete. So why is the current approach not complete?
It's not complete because the transition out to another is take by the current state and rapid synthesis the environment place first. So we are one environment place before we have to take the decision to jump or not to another mode. So if jump correctly to another mode, the environment can win us. For example, here I have an example. We have MC, we start in M0, then we can go, when we are in M1, we have to go back to M0, and then if we are M0, we can stay or we can jump to another mode. It all depends on the environment variable E. So if we are in M0, we can decide to jump M1 just because we decided before we saw the environment place, and fortunately, the environment place know it. So there is no violation of the specification. We go back to M0, and now we decide to jump the environment place E, and we decide jump to M0. We stay in M0. So it was a fortunate moment, but it can lead to imagine reports negatives. So always the correct way to do that is using mode determinism, that is basically using some kind of table like SCR methodology on where the movement of the environment, the transition to a new mode is only determined by the current state of the system, no matter what the environment plays in the next. And thus, like we are one environment place before. So that's why it's incomplete, but we are trying to make it complete.
Good, thanks a lot. If there's no more questions, let's thank the speaker again.
then our last speaker of the session. So we have Mohit Tekhival from Lawrence Livermore National Laboratory speaking on mechanized semantics for correctness of RS 274 additive manufacturing command language. That's a mouthful. The floor is yours. Thank you.
Thank you so much. Yeah, so today I'll be presenting our work on mechanized semantics for correctness of RS-274 command language. I'll start by introducing what additive manufacturing is. So as opposed to conventional manufacturing like milling, lathe, and drilling, where some parts of the tools are removed to obtain the object, additive manufacturing techniques, they deposit materials layer upon layer in precise geometric patterns to create tangible objects. And there are typically 7 kinds of additive manufacturing processes. But in this talk, I'll focus on material extrusion, wherein the filament is extruded from the nozzle to deposit the layers and obtain the object. There are different sources of errors in additive manufacturing, which are classified into these 3 categories, which include the software error due to errors in tool path finding software and errors in processing software, kinematic and geometric errors due to collision detection and thermally induced errors, and configuration error due to human errors in specifying coordinate information or poor selection of feed date, etc. In this talk, I'll be talking about a subset of the software error, which is the errors in tool path planning software. There are 2 common approaches of validation in additive manufacturing, simulation with visualization and physical examination of the artifact after fabrication using destructive and non-destructive testing. Each of these techniques have some limitations. For example, visualization can detect issues arising from incorrect rates or temperatures that can affect material properties. And high fidelity testing can be very expensive and time consuming. So our approach to remedy this issue is to do a direct analysis of the tool paths, which can help us detect some certain issues. And to our knowledge, there has been no prior work on tool path software verification. Now, in terms of where our work lies in the whole 3D printing pipeline, I'll briefly go over the workflow of 3D printing processes. So the first step is to design a CAD model in a design software like AutoCAD, SolidWorks, or Autodesk Maya. And once the 3D model has been designed, that can be exported as an SQL file, which then goes to a slicing or tool setting software like Ultimate Cura and Simplify 3D. And this is where the tool paths are generated, which is actually machine instructions that go to a 3D printing device firmware. And these tool paths are called the G codes. And our work is in this last stage of the 3D printing pipeline, where we analyze the tool paths of the G codes. And this is very important because these are the actual tool paths that are being used for printing, and any corruption in the thread path can actually disrupt the integrity of the print. Now, to analyze these G codes, we start by looking at this standard called RS-274 NC standard, which was initially developed for conventional manufacturing, but has later been adopted for unconventional or additive manufacturing techniques like 3D printing. And this standard or this language by itself is based on a line-oriented execution model, where each command may include commands to perform tasks like move the printer head in a straight line or in a circular arc. And the words for these commands are called the G codes or the M codes, where G codes mostly operate in the physical state of the machining tool, like a linear motion or naked circular motion. And M codes, they mostly operate on the controller state, like extrusion and coolant, etc. And in this, on the left-hand side of the slide, I have shown what the example of a G code, which is used for printing the square. So as you can see, these are just set of straight line instructions, where the first line, G90, essentially specifies the reference frame. So all the coordinate updates in this case are with respect to an absolute frame. And the G1 commands are for straight line motion. So in this case, if I say G1X 1.0, this means that starting from this origin, the printer moves 1 unit in the positive X direction, and G1 1.0 would mean that the printer moves 1 unit in the positive Y direction. And so we can trace this code square using the straight line instructions. Now, this G and N commands, of course, are further classified into two categories, which are called modal commands and non-modal commands, where the modal commands have the effect persistent, I mean, even after they're specified in a given line. So if no other modal command is specified, then the effect of that modal command will persist throughout the set of instructions. So for example, like G90 and G91 are set of modal commands. If I have G90 specified in the beginning of the file, then all the coordinate updates will be done with respect to an absolute frame of reference. But at some point, if I specify G91, then all the subsequent coordinate updates will be done with respect to local frame of reference, which is attached to the machining head. Yeah. On the other hand, we have these commands called non-modal commands, which have the effect restricted to just the line in which they occur. An example of that is G92, which is for specifying center offset. So if I have G92 with some access values, those access values will be set as the center, and the coordinate updates will be done with respect to that center. But that setting of the center is done only once. Yeah. And this modal commands are further classified into groups called modal groups. And the transition in each modal group does not affect the transition in the other modal group. As an example, I have two modal groups here. One is for distance mode, and the other one is for predate mode. And you can see here there is no transition from distance mode modal group to predate modal group. All the transitions are within that modal group. So there's a transition from G90 to G91, and from G91 to G90, and in the predate as well, we have transitions between each mode within that modal group. Furthermore, if you notice, you can notice that some modal commands are circled in gray, whereas other ones are in white. So that means, so what that means is that this modes which are in gray, these are the default modes for that particular modal group. So you have, in the case of distance mode, G90 is set as the default mode. So if I do not specify explicitly any command for distance mode, then by default it assumes that we have set the distance mode to absolute. Whereas in the case of predate mode, there is no default modal command. So you'll have to specify explicitly which of the modes you want to set. So there are a lot of subtleties in modeling this modal states, and a lot of work that we did was like carefully modeling this transition diagram. So in terms of the high-level interpreter design, our tool takes as input a G code, which is obtained from a Symposium tool comparing software. We have used a thing like a Cura, where we gave an object and we obtained the tool paths, which was then passed into an AST that we have defined in our tool. And the interpreter loop would essentially go through each command sequence in the AST. And the interpreter step function would then step to obtain a new state, which then goes to this VC checker, which is a verification checker, which enforces some domain-specific constraints. For example, the machine's head is inside a bounding box or not. And if this VC check has been satisfied, then the interpreter loop will go to the next command sequence, and this loop will continue until we reach the end of the line, in which case we get a successful execution phase. But if at some point this VC check is violated, then the loop stops and it will generate a failure report, which will tell where that error has occurred and which condition has been violated. And the nice part about the design is that our tool is modular in the sense that we can add different verification checks without impacting the rest of the interpreter. And in terms of the property that we have verified, the key correctness property about this interpreter that we have verified is that if certain well-formed conditions are satisfied on the configuration settings, which are inputted by the user, and the RS-274 NVC command itself, such as the value parameter handling for each GN encode, and if certain physical and moral state constraints hold, then the interpreter will yield a resulting output state which satisfies those state physical and moral state invariants, or it will fail, which will yield a, fail and yield an error message. So we have mechanized this correctness theorem in the rock theorem prover, which looks something like this, where we have well-forwardness for the configuration as a precondition, some predicates on the implemented ASP code words, as well as preconditions, and some invariants on the modal and the physical state, which needs to be satisfied for the input state and for the output state as well. So next, I'll go over each of those components. So I'll start by discussing the configuration. So in this case, inputs the interpreter such as modal and non-modal groups, G and M commands in these groups, priority order of these commands in the modal and non-modal groups, coordinate extensions, vendor-specific extensions. They are specified they're specified in a configuration file as JSON objects, and our tool will take those configuration file and convert into an OCaml data type. And we need to ensure that the configuration parameters are well formed. For example, the modal groups are disjoint. So if you remember the graph, that would mean that the distance mode and the feedback mode modal groups are disjoint and there's no transition. Modal commands, they belong to the right modal group. And we also have the totality of the modal and non-modal command. What that means is that if a code is a G code, then it either belongs to a modal group or a non-modal group, but it cannot belong to both of those groups. And also we have validity of the modal group. By that we mean that the data structure that we use in this case, a string map data structure to model the modal groups and the commands, they have a unique key value per electric group. And so we have taken all these conditions and specified that as a precondition for our correctness theorem. The second thing is a predicate on a subset of the ASP code words from the ISO74 language that we have that are relevant to 3D printing that we have implemented here. So if you remember, a permissible line of the input ISO74 code contains a set of version parameters, and each line is then parsed into an ASP that represents this code words as OCaml data type. And this implemented ASP-con, this definition essentially associates a predicate with each of the code words that we have implemented. For example, finiteness condition on the access values, the radius values, and for the general function and miscellaneous functions, we have some additional things like the validity of the parameter handling, the right code words for each of belonging to this groups, and again the finiteness conditions on the predicate. So the third thing that we need to ensure that we mechanize is the parameter handling itself. So each of the access code words have an associated value, which informs the printer how much it needs to move in each direction. For example, x2.1 informs the printer head that it moves 2.1 units in the positive x direction, and these code words have some constraints associated with the parameter handling, which are informally specified by the ISP74 standard, which are mechanized. And in this case, we have mechanized a couple of constraints. The first one being that the access values, which are represented as float, should be strictly finite, and the access code words would have at least one access value specified. That is, at least one of the x, y, or z axis must be specified. If none of them are specified, then that would result in an error. Next, next is state invariance, which need to be satisfied with both input and output states. To discuss state invariance, I'll first discuss the state model of the interpreter. So the top level state here is the machine state, which is decomposed into a physical state, which holds information like timing, positional value, path history, and exclusion. And the controller state, which is further decomposed into a controller physical state, which handles all the parameters, access parameters, and the modal state, which maintains those list of modal commands and the groups which are associated with the machine kinematics. And the key to the design of our interpreter was this nice decomposition of the machine state into different components, because that would allow us to use different provers to do these proofs over different components, and then we can later compose them together to obtain our data interpreter. So I'll start by discussing about the modal state invariant. So the key invariant that needs to hold here is that two members of the same group cannot be active at the same time. So what I mean by that is, so in the case of the distance mode where we have G90 and G91 commands, both G90 and G91 cannot be active at the same time. Either G90 is active or G91 is active. And since in our implementation, we maintain this model group as a list of key value pairs, where key include the model groups such as motion, distance, and plane select, and value represents the corresponding G codes. This state invariant boils down to proving the uniqueness of the key value pair. Yeah, so the second state invariant is about the control physical state, which maintains its access parameters, feed rate, extrusion, and coordinate offset. And the invariant here is the strict finiteness of this physical value. Similarly, for physical state, which maintains the positional values of the printer head, length of the filament, path, etc. Again, the constraint is the strict finiteness of these physical values. So essentially, what we have covered so far are the various components that occur in the correctness theorem. But to do the proof, we have to go through each of the command sequence in the AST and design about the correctness of each of those. So two things. So there are two main functions in that is in a command sequence that we kind of that I'll be showing the correctness theorem about, which are the M commands and the G commands. So start with a discussion on the semantics for M commands. So M codes, they mostly affect the controller state like program, stop, tools, etc. And they do not have any side effects on the physical update of the machine. So if you can parse this, the statement of the interpreted correctness theorem that we have in talk. So what this states is that for a given configuration, a machine state code word, the model state invariant needs to hold for the input state, and you have the right code words that belong to the model that belongs to this M model group. So in this case, 82 are for the extrusion. So if these two invariants hold, then the final state will also respect the model state invariant. Furthermore, there is no update done, no physical update done to the output state. So the final state and the initial state, they have the same physical properties. And key lemma that we have proved in the correctness of the semantics for this and commands is the correctness of the modal updates, which means that if the input state, if the modal state invariant codes for the input state, after I have done the update, a new modal state, the new modal should also respects the state invariant. Next, I'll discuss semantics for the G commands. So the G commands are categorized into two categories. One corresponding to the modal states only, which include commands related to plane select and the distance mode. And the second one is related to the physical states, which includes commands related to motion and coordinate reset. So as the first one that we'll be looking here is the plane is the G commands associated with modal updates. So there are two such G commands that are implemented. One is the plane select, and the second one is the distance mode. So in this slide, I have a talk definition of the correctness for the plane select. The distance, the correctness lemma for distance mode is very similar to the plane select mode, except that we replace these code words 17, 18, and 19, which are reserved by the RS-274 standard for plane mode, with the ones that are relevant to the distance mode, which are 19, 91. And also we replace the modal group plane select with the key motion. So as you can see here, again we have those properties that that this plane select mode does not impact the physical does not impact the physical state of the machine and the controller. The next set of G commands that we have looked at are the ones corresponding to physical updates, and there are three categories of those G commands. One related to linear motion, second one to circular motion, and the third one related to coordinate offset. So for the linear motion, the ISO 74 standard they reserve these two G commands, G0 and which is for rapid motion, and G1 for coordinated linear motion. Semantically, G1 is very similar to G0, except that G1 allows the machine to move at the feed rate, whereas G0 allows the machine to move at the motor speed. So feed rate and motor speed are essentially the speed at which the machine head will move, and those two are different. There's a very subtle difference. But since in the first iteration of our tools, we did not model the speed, feed rate, and motor speed, we assume that the semantics of G0 and G1 are exactly the same. The correctness for this linear motion is represented using this state diagram. So it states, so we have the pre and post formation associated with the transition. It states that for the initial state, if the preconditions state invariant by parameter handling and strict finiteness of the vector operations that hold because we are doing because we are updating the physical state as well. So that involves vector operations. So this precondition hold, G0, G1 executes to obtain a new state, then the new state also respects the state invariant. For the circular motion, ISO 74 standard reserves the two code words G2 and G3, where G2 is for clockwise motion and G3 is for anti-clockwise circular motion. And the semantics for G2 and G3 are also same except for the sign. And the correctness lemma that we have is parametric with respect to the sign, where we associate the value 1, like the positive 1 with G3 and negative 1 for G2 for the signs. And the correctness for this circular motion breaks down into proving the correctness of these two specific formats that are specified by the standard. And this essentially says how the objects are being made. So there are two standards, one corresponding to the center arc move, where the coordinate information of the endpoints of the arc is specified along with the offset values, where the offset values are with respect to the starting point of the arc. And these offset values are used to determine the center of the arc. So this endpoints and offset values are specified in the center arc move, whereas in the radius arc move, the coordinate information about the end point of the arc and radius of the arc is specified. And we have to prove the correctness of these two formats and then compose them to get the correctness for the detail. So the state diagram for the circular motion is very similar to the linear motion, except that we have two more preconditions. One is about the validity of the parameter of the plane select mode, where this where the validity condition means that plane select mode is deemed valid if the plane modes are G17, G18, or G19, or none. None because the default is set to G17. So if we have none, then essentially we have the G17 is invoked by the interpreter. And the second condition is specific to the how access parameters are handled in both the formats, center arc and radius arc. So for the center arc, it says that at least one offset value needs to be specified. And if none of the offset values is specified, then essentially it will result in an error because we cannot compute the center of the arc, and hence the arc motion cannot be defined. Similarly, for the radius arc format, we need a radius value, and it should define it. Otherwise, again, we cannot compute the arc. So we need we need these conditions to be satisfied for the arc motion that we do value. To summarize, this right hand, so this diagram on the right hand side, it kind of shows the dependency chart of our different components of our formalization. So the yellow boxes are the ones that represent the parts that you have mechanized in the Rockson prover, which mostly include the algebra operations and other proofs about the proofs about the correctness of the semantics for different instructions that I have shown earlier. And the green boxes represent the parts which have been mechanized in the Rockson prover, and those include the proofs about the data structures that we have used to maintain the model state. And in terms of the extraction, so we have approximately 54% of the code that has been extracted and verified from Y3 and Rock, and the rest is unwritten, but we also make sure that this can be verified. So the future was good in verifying these different components as well. And in terms of the lines of block group, you have approximately 15,000 lines. So to conclude, in the first prototype of our interpreter, the focus was on mechanizing and extracting a subset of those ISO74 commands which are relevant to 3D printing. And to make this tool more complex and more practical, we are working on different directions. So the first direction that we have taken and we have finished is incorporating uncertainties from physical noise. So in this particular case, we have used the STAN probabilistic programming language to model the uncertainties in the dynamical system, and we obtain like a bound on each associated with each coordinate value that will give us some uncertainty interval that we can use later to do proofs on collision detection and this kind of stuff. The second thing that we are currently working on is on automating a lot of stuff because most of the proofs that we have done in the first iteration are interactive. So one thing that we're looking at is implementation of fixed point, replacing floating point with fixed point because most of the domains are bounded. And the second one is exploring the use of AI for doing some proof automation, especially related to the static concept. The other direction that we are currently working on is extensibility to vendor-specific report extensions. So we're using virtual machine-based approaches to decompose the parts that are separate from this kind of extension. And the fourth work and the last thing that we are currently working on is integration of more domain-specific text, such as collision detection, and we are using things like bounded value hierarchy or KDQs to do this kind of to implement the collision detection text. Yeah, so that concludes my presentation. Thank you for attending, and I'll be happy to answer any questions. Thank you.
Thank you. Any questions?
So can you go back to your slide of the conclusion? So
Which slide, sorry?
if you can, the conclusion, the previous. Yeah, so it said that you are going to consider incorporating uncertainty from physical noise. So I guess that we could use the same technique for incorporating uncertainty from fixed floating point arithmetic round of error.
Yeah, I mean, the idea was to use some kind of sampling-based approaches. Use sampling-based approaches for doing this kind of uncertainty reasoning, and that's where we kind of look at using probabilistic languages like standard to allow us to sample the values within, and then that would give us like a value, and we can just use that for doing things like collision detection. We have some fuzzy value around exact part trace, which can help us select the collision.
Okay, and in your proof in code, did you assume exact real arithmetic logic?
No, we assumed proofs. We worked with proofs. Yeah. So the thickness is essentially deriving some bounds on the input or the conditions, which would ensure that we are always within this fixed finite matrix, and we do not have those exceptional values. Those are like the preconditions for each of the commands. Yeah.
Thank you.
Thank you.
Other questions? I have one, maybe it's a stupid one, but I am working with hybrid systems, so I was wondering all the time, how do you manage the discretization? Because your invariants require this strict finiteness, but normally it's all continuous variables, right?
Right. Yeah, so right now, yes, we assume continuous times, we not assume the discrete ones.
Sorry?
So we assume like the continuous dynamics, not assume the discreteness right now. Yeah. So yeah, like for the linear circular motion, we assume that it's continuous instead of a discrete.
And your result is still correct, so it doesn't impact the quality of the result?
So the quality, yeah, that's what we are trying to do with the adding some checks to see, so right now, since most of the updates are like vector updates and stuff, so the checks that we have implemented are just the finite matrix. We did not assume the kinematics. So when you start implementing the kinematics, that is where we might run into the discrete continuous.
I see. Okay, cool. Thank you. Any more questions? Then let's thank the speaker again. That ends the session, right?
So yeah, this was the last session of this morning. See you at 1:30 after lunch.
Hello, everyone. Welcome back from lunch. We are very excited to start the hybrid systems track here. We have 3 exciting papers coming for you. And the first one is by Jainta Paul. We're going to hear about HiTwin, hybrid program semantics for digital twin-based security interventions in industrial critical systems.
Good afternoon, everyone. I am Jayanta Paul. I'm a PhD student at the University of Utah and a member of IOTrust lab there. I work in the intersection of formal methods and industrial control system security and also artificial intelligence. So today I am going to present our work, HiTwin, hybrid program semantics for digital twin-based security interventions in industrial control systems. Our lives actually depend a lot on industrial control systems, like the water treatment plants give us fresh water, and then nuclear reactors, power grid, they give us electricity, and also the factory automations, they are useful too in our lives. Often these plants become victim of cyber attacks. The most renowned of them is the Stuxnet malware that performed adversarial actions against a nuclear reactor in Natanz. And then there are power grid attacks, cyber attacks in Ukraine. And in the United States, there are a lot of, there have been known to be many water treatment plant attacks, and they all have like devastating physical consequences. So it is important to know how these adversarial actions are performed and how can we detect this kind of attacks, and not only detect but also mitigate the consequences that happens due to these attacks. To know how these attacks are executed or how can we detect this kind of attacks, we have to know the components of a industrial control system and how the components interact with each other. And there is no better way to explain the components of an industrial control system than the Purdue model. What the Purdue model provides is it provides a standard of for which how the components of an industrial control system should interact with each other. For example, this is the Purdue model of an water treatment plant. So at the top, we have the administration laptop and the business server that interacts with the next level, that is the historian and the engineering server. And then there is the HMI, which is the human machine interface, and SCADA, which is the supervisory control and data acquisition system. They interact with the programmable logic controllers at the next level, and then they interact with the physical components like the valves, pumps, the transmission pipes, and other physical components. Typically, the programmable logic controllers are responsible for performing the physical tasks. Like in this water treatment plant, the programmable logic controller PLC1 is responsible for transferring the water from raw water tank to the dosing tank. And it does so with the help of the water level sensors, the valves, the pumps, and the other physical parts like the transmission pipes, etc. And the question is how the PLC performs this complex physical task. It does so with the help of scan cycle. So a PLC continuously scans for input from the sensors. Based on the sensor values, it changes its execution logic, and then based on that execution logic, it performs the physical task through actuators like the pumps or valves. So when the physical task is being executed, the values of the sensor changes, and again the PLC takes the new value, and again it changes its logic and executes that with the actuator. And PLC does so continuously until the plant is shut down or the normal operation cycle has been completed. Now we'll see how an adversary can compromise some of these components here. For example, sometimes in the water treatment, for example, this water treatment plant, the HMI or any other components, if it were exposed in the internet, the adversary can penetrate into that and actually cause some malicious activities. So the adversary can perform the penetrate into the either the administration laptop or the HMI, and then from there it performs reconnaissance, which is learning about the layout of the system, and ultimately it gets to the programmable logic controller. So when it gets to the programmable logic controller, it can perform a vast number of malicious activities. Like it can shut down the plant, it can shut down the pump or the valve, it can spoof the sensor to a wrong value that is not what it's supposed to be, and it can actually in this case, for example, it has the capability uh, to spoof the sensor and the valve. So the question becomes, how do we detect this kind of adversarial actions? And there has been many techniques for detecting this kind of attacks. But one approach that has gained a lot of attraction in recent years is the digital twin. So let us learn a little about the digital twin. A digital twin is the virtual replica of the physical twin, that is the physical system. It interacts with the physical components, and based on some initial values of the physical system, it predicts the next values. It monitors the values of the system, and based on that, it judges if there has been an adversarial action or not. For example, in this case, the digital twin monitor will interact with the physical water treatment plant and then decide if there has been a malicious attack or not. The problem with digital twin is it depends too much on the physical dependencies among the variables. And if the adversary is so intelligent that it spoofs the value in a way that the digital twin cannot detect it, then the physical safety properties will be violated. So let's see an example here. Let's consider that an adversary has spoofed the water level sensor X1, and also it manipulates the valve to remain open when it should not be. The goal of the adversary here is to cause overflow of the water. And you can see this timing diagram here. The red dotted line represents the spoof sensor value. The green line here represents the actual tank level, and the black line represents the value predicted by the digital twin. So as you can see, if the adversary spoofs the sensor here and keeps the valve open and spoofs in a way that the digital twin detector cannot detect it, by the time the digital twin detects it, it will be too late. See, so most of the digital twin will predict the attack here, but by the time it predicts, like this amount of time has been passed. So for this reason, we need a way to not only detect attacks, but also force mitigations. And even if some attacks may not be detected, how can we ensure that the safety properties will be maintained? So that is where our framework comes in. So we introduce HiTwin. Let's take a look at the overview of our framework. We have a database of known attacks and verified mitigations. From these known attacks and verified mitigation, we have a digital twin monitor that monitors the physical system here. And based on those known attacks and verified mitigation, the digital twin tries to find an attack signature. So after the digital twin finds an attack signature, we try to calculate the mitigation horizon. The mitigation horizon tells us how long do we have before a safety is violated. And we calculate it anyway, be it an adversarial scenario or a normal operational cycle, we calculate it anyway. After we have the verified mitigation, and if we can detect an adversarial action, we force the verified mitigation into the system. For example, this is the same water treatment plant I was talking about earlier. Here we have an adversary that has manipulated the valve and the sensor. And in the database, we have stored the verified mitigation, that is draining the water by keeping the valve, the next valve V2 and the pump P2. So that is how we prevent an overflow, but we will see details later. And we have formally defined each of our components in the paper, but we will also give an overview later in the slides. A little clarification here. Someone might think that we may need a large number of concrete attack database, but that is not actually true. We will see later that one attack program, we defined attack program, one attack program can represent a large number of concrete attacks. And the mitigation, as soon as we detect the attacks, we will force the mitigation immediately. But if we cannot, if some attacks may not be detected, we will explain later how we can maintain safety in those scenarios. And for our framework to work, we need some assumptions. We assume that the digital twin cannot be compromised. Mitigation logic is verified and will work. The mitigation channel, it cannot be compromised. The adversary can compromise the sensors, actuators, even the PLCs, but it cannot alter all the components at once. And the adversary cannot alter the digital twin model or the mitigation channel. So visually representing in our framework, these are the trusted components, and these are the components that are vulnerable or can be compromised by the adversary. So with these assumptions in mind, we will see how we can model the safeties of an industrial control system. So this is the same water treatment tank that I was talking about, and it has a safety property in terms of the water level. The safety property is that the tank level, it cannot go beyond the upper threshold, and it cannot go lower than the lower threshold. It has to maintain this safety property. So across infinite amount of executions, let's say, how do we ensure the safety is here? There are two ways to think about that. For example, let's take a look at the diagram here. We can say that the flow rate is either 0 or a concrete number based on if the valve is open or closed. But the thing is, in industrial control system, due to physics-based uncertainty, the flow rate can be anything between 0 and 5. It can be any number, any continuous number. So let's say the flow rate is a non-deterministic number. And how do we now ensure the safeties? We model the industrial control system as a hybrid program, where the continuous actions are the physics-based actions, like let's say the water level changing from 0 to the upper level threshold. And the discrete actions are the control logic actions, like let's say toggling the valve or keeping the pump shut, etc. We say that for all states in psi, for all states alpha, psi holds true, and psi is the here the safety property. And this is our safety property in terms of the water level. And we say it will hold across all the states that is comprised of the physical dynamics, that is the plant, and the discrete actions, that is the control logic. Here we have shown what are the continuous dynamics and what are the discrete actions. And we say that these safety properties will hold across infinite amount of executions as long as we have a initial property that is true. And the initial property here is that initially we assume the system is in safe mode, and the flow rate, which is the tank level, is between this limit. So we can actually decompose these states into scan cycle normal form. This was a work done in high PLC. Actually, the combination of control and plant has been decomposed in a way that looks like the scan cycle. But one thing high PLC did not introduce is what will happen if we introduce an adversarial action here. Did not model the adversarial action. So let us see how the scan cycle looks like if we introduce an adversary here. For that, we define an attack program. An attack program is a hybrid program, AI, that models adversarial control of our sensors or actuators or other cyber physical components. For example, the same attack that I was talking about earlier, we define the attack program here as V1, 1 and X1, X tilde minus delta, which is, this is the spoof sensor value, the value that the adversary has injected into the sensor, and this is the real sensor value, and this is the valve. Now, define system under attack. That is, if we introduce this attack program, how will the system look interact, or how will the system look like? Again, this is the scan cycle, the normal scan cycle without any adversarial actions. And if we introduce the same attack here, this is how it would look like. Now we have, the system has two choices, either the normal control or the attack program. In this way, we have modeled the uncertainty. We don't know when the adversarial action will happen, but we have modeled this anyway. Now we define, let's take a look at some of the attacks that cannot be detected by the traditional detectors. For that, we define the attack detector. The attack detector, an attack detector is a predicate that evaluates to true if the system appears safe, and false, it exhibits behavior inconsistent with the expected model. So simply put, an attack detector will detect an attack based on some logic. If it can match the logic, then it will raise the alarm. Otherwise, it will not raise the alarm. For example, this is the same attack that I was talking about. And let's say we have a detector and it detects the attack based on the spoof sensor value and the predicted sensor value of the digital twin. And it will raise an alarm if the difference is greater than this detection threshold. But if the adversary is so intelligent that it manipulates, spoofs the sensor value in a way that it remains less than the detection threshold, then the detector will never be able to detect the attack. So we define stealthy attacks. An attack is stealthy if it does not violate the detector predicate, and eventually it will violate the safety properties of the system. So like the sensor attack that I was talking, this is a stealthy attack. It will evade detection of the traditional detector, and if any actions are not taken, then it will violate the safety properties of the system. We will see how our framework can maintain safety even if we miss detecting these kind of attacks. So this is central to our approach, the mitigation horizon. We will define the safety horizon and the mitigation horizon here before explaining how our framework can maintain safeties in this kind of scenarios. To define safety horizon, the definition is let alpha be a timed hybrid program, and if P be a safety property, the safety horizon is the maximum time during which executing alpha from the initial assumptions it guarantees P. Beyond P, no longer holds. And based on the safety horizon, we define the mitigation horizon, which is, let's say a mitigation program, let's say a mitigation strategy be MX, and we say that mitigation horizon is the latest time after executing alpha when applying M still restores the safety condition S. So this is central to our approach. This essentially tells us how long do we have before the safety property is violated without any intervention. So now take a look at the same example that I showed earlier. This is again the red dotted line represents the spoof sensor value. The black line represents the level predicted by the digital twin, and the green line here represents the actual tank level. So at this point here, we have the mitigation horizon as calculated, for example, as 17.5 seconds, and the policy threshold is 3 seconds. So policy threshold is something that should be set by the administrator if the mitigation horizon at some point becomes less than the policy threshold, then we will force mitigation into the system. So the next point, the mitigation horizon becomes 12.5 seconds. That is, this is how much time we have for mitigation. And the policy threshold is still 3 seconds constant time. The next point, it becomes 7.5 seconds. And then the next point becomes less than the policy threshold. So at this point, we force the mitigation into the system, and this is how we keep the system safe. In the paper, we have described more complex scenarios where the adversary can manipulate more components, and we have shown that formally verified mitigation logic works in many complex scenarios and keeps the system safe. So, conclusion, we have introduced high-twin attack modeling, that is, we formalized attacks and mitigations as hybrid programs in differential dynamic logic. We compute time bounds for safe intervention under ongoing attacks. And we introduced synthesized monitors and certified mitigation for probably safe runtime response. In future, we want to model more scenarios. We want to integrate this framework with existing industrial control system engineering and simulation. And we want to generate attack monitors and mitigations from high-level specifications. So yeah, thank you.
Thank you very much. Do we have questions? I'd like to start with one, actually. If you can go back to the first slide where you showed the graph of the actual tank level and the digital twin predicted,
Yes.
and the attacker inserted one. I was wondering, what is the reason why the digital twin was, it looks like it's almost as much below the actual tank as the inserted attacker level. Is there a reason why they were off like that? Is that like just a normal thing, or why is there a gap?
Okay, that is a very good question actually. So we have modeled an adversarial scenario where the attack can be stealthy, and we have assumed that the attacker will spoof the sensor in a way that it remains stealthy. That is too intelligent to violate the safeties, and again too intelligent to miss the detection of the digital twin. So that is why we modeled it like this.
So in some ways, the attacker is affecting the values returned by the digital twin here.
The attacker is actually not violating the values returned by the digital twin. It's actually violating the values the actual values. In this scenario, the sensor itself is compromised.
Right.
We know the actual tank level, but since the sensor is compromised, so the digital twin sees the spoofed sensor value.
Yeah.
But digital twin, since it initially we thought that the system remains safe before even the operation started. So digital twin, from its physics-based model, it calculates the value based on the initial value, and it does not actually need to rely on all the continuous values across the executions. If it makes sense.
Yeah, I think I understand better now. Thank you. Do we have another question from the audience, or I have more questions? I'll give you guys a chance. Okay, awesome. Well, then I will ask my other question.
Yeah.
You had on your list of assumptions that the attacker could not affect the value of the attacker capabilities, that it cannot alter the twin model or mitigation channel. I was wondering why. I mean, I get why you might want that, like to narrow in on what you're doing here, but is there a scenario where you would open that up? Because it seems like if I'm an attacker, maybe that's the easier path, right? Like maybe I want to attack the digital twin just to throw you.
Yeah, that is actually a very good question. Actually, this is something that we will explore in future when we incorporate more complex scenarios. And one of the scenarios would be modeling what will happen if the digital twin itself is compromised. So at the top of my head, one solution would be to get a backup of the system of the digital twin modeling. And then while it monitors the original system, that digital twin monitor will monitor the digital twin itself. But again, we will have to incorporate that in future formally.
I look forward to reading that, maybe next year at NFM.
Yeah.
The digital twin attacker
Yeah.
scenario. All right, sounds good. Yeah, all right, we have questions.
Yeah, I wanted to. I saw that you modeled in the differential dynamic logic. Did you use Chimera to do some properties on your system? Yeah.
Yeah. I did not mention that, but yeah, we use that. So we actually modeled the adversarial program, and then we fed that into the KMRX so that that is compiled and verified. The mitigation is verified with respect to our time bound. That makes sense.
All right, great. We'll thank our speaker again. Thank you so much. You can have the next speaker come up. All right, next we are going to hear a talk by Jane Xiang on extending dynamic logics with first-class relational reasoning. Go ahead.
Thanks. So first of all, I want to say thank you for the first talk because the first talk basically laid the foundation for many of the stuff I'm going to talk about, and more even better, the first talk actually cite our paper from previous years. So we have a lot of overlap, and I actually worked on hyper programs and venture dynamic logic for security purpose. So, okay, coming back to reality. So in this work, we are doing extension for dynamic logic to support first-class relational reasoning. As the slides indicate, my name is James Xiang, and I come from UNC Charlotte. I'm a junior faculty member at the security department. This is a joint work with my former advisor at Harvard, Stephen Chong. So for the last probably 5 to 6 years, now I've been working on this thing called relational properties. And to give you a little bit more context, the reason for this work basically was motivated by all the stuff I have seen over the years, including mostly security properties. So we came across different properties we want to prove within, especially cyber physical systems. Then in doing so, we want to have a powerful tool which allows us to do verification of relational properties. And the relational properties are properties over pairs of traces. There are two categories of relational properties. The first one is properties comparing two traces of a single program or system. The second category is properties comparing traces of two systems or two programs. For the first one, we have a well-known security property called non-interference, which is basically guarantee that publicly observable channels do not leak confidential information. So it's mostly about confidentiality and integrity. So we can formulate this non-interference property as a relational property, which basically says if the program takes two low security inputs, the same low security inputs, the program will produce the same low security outputs. In other words, it means the low security outputs do not depend on the high security inputs, which usually is the high security information or confidential data. For the second category, we have examples of refinement relations, which basically says one system has all the behaviors of another. And the robustness, which is what I have been working on in security domains for the last few years. We try to do secure analysis on the attack in terms of how to prove robustness. It usually says in our knowledge is about the relationship between a compromised system, the system under attack, and the original system. So if the compromised system performs the same as the original system, we say it is robust against the attack. We have optimizations, which is basically optimized program runs faster than the original program. Then many other programs, many other properties. For example, you can think about other stuff like the deterministic, which is actually something you can specify as relational properties. The challenges we face with relational properties are twofold. First, usually they need to express with some heavyweight logics. The second one is, more importantly, we need tools to verify these properties. As far as I know, we have some tools which are decent, but we still lacking a lot of effort in this direction to powerful verification for complicated relational properties. So the goal of this work is to build some foundations we can continue working in the next few years to build powerful verification tools for relational properties. So in this work, we contribute the general relational extension for dynamic logics with two goals. First, to express relational properties intuitively and concisely. So we want you to be able to see when I lay down this relational property, then you sort of directly understand what I'm talking about. So to do that, I use a program construct called byprogram. We add a pair of programs, which is this alpha and beta, which we call the left and the right programs. So using this byprogram construct, we directly have two programs. Then the second goal is to promote practical verification and automation, the automation of the verification. So to do this, we basically reduce relational verification to safety verification, meaning we sort of rewrite the relational formulas into the formula of the host logic. By doing this, we can reuse existing tools for the host logic. Here, I'm going to also use Chimera X for relational verification, which is what the tool used by the first talk. So in addition to reusing existing tools, we integrate different techniques, reasoning techniques, into this reduction process. So the purpose is to make it more powerful, obviously. So after this reduction, we can produce formulas that we can verify easily with Chimera X. We conduct two case studies. The first one is on differential dynamic logic, which is basically hybrid programs, the one we see in the first talk. It is a logic for safety verification of hybrid systems. The other one is called linear dynamic logic, which is temporal style logic for AI community. They use it for planning purpose. It's actually sometimes I prefer to call it linear temporal logic plots, something like that. So, in this talk, I'm going to focus more on DL, differential dynamic logic, and I'm going to introduce the syntax, which you already have seen a little bit, and semantics. And then I'm going to use some examples. I'm going to spell you all the technical details of the semantics. I'm going to give you some example on this relational extension for DL. Then I'm going to talk about verification support, how we verify the formulas expressed by these relational extension. You can find more in an extended version of this paper, which covers the other case study on linear dynamic logic and another encoding. When I say encoding, what I mean is you encode the relational formula as the hosted logic formula, which allows you to reuse existing tools. This encoding is actually quite interesting. Even I didn't really put it in the paper for this one. This coding is actually using SMT solvers, and the performance was quite good actually. So let's start with DL. So we already have seen a little bit. This is the syntax of DL. It is defined inductively on programs and formulas. The semantics of formulas is defined as the set of states that satisfy the formula. What you have in the formulas include comparison between two terms, negation, not surprising, conjunction, also the conjugation, and the one we have seen, the what we call the box modality, and also referred to as program necessary. So what this means is for this kind of formula satisfied by a state omega, if for all possible execution starting from state omega, or all possible execution of program alpha, the reachable state will satisfy the formula phi. So intuitively, it means for all executions, we will satisfy the formula phi. Its dual is what we call the diamond modality, which is program existence. The two can be used to encode each other. So I didn't really put it in as part of the syntax because you can do the encoding by yourself. What it means, obviously, is to say that exists some execution of program alpha, which will make the formula phi hold. Here we have for all execution, here we have for some execution. The program construct in DL includes determining assignments, which assign a value of this term. This term is a real value term into the X. We have non-deterministic assignments, which assign an arbitrary value to X. Then we have this structure, which we've seen in the first talk. It's a special program construct modeling dynamics of CPS. The meaning of this construct is given the initial value of X, the system follows the differential equation X, the derivative of X equals theta for an undeterminate amount of duration, as long as formula phi holds for that duration, for all of that duration. So in addition to this construct, we have operations from clean algebra with tests, including testing for formula, sequential compilation, non-determinate choice between two programs, and the repetition. Okay, so in general, the form of CPS, as you already see, it is modeled as an unbounded repetition of controller actions followed by an update to the prompt, which is the dynamic. And here, the program control usually models atomic control actions, and the program prompt models the dynamics using this structure. Okay. The property within DL, the property we usually interested in this way. So this safety property means given the initial condition, which is phi free, after all possible execution of this program, of the system. This is the program model of the system. After all possible execution of the program, the system, the safety condition phi safe is satisfied. Okay, so this safety property we usually concern within DL. A quick example using a very simple autonomous vehicle. This vehicle tries to avoid collision with the obstacle. So we have distance to obstacle, we have velocity, acceleration. Then the controller is modeled by undeterminate choice between acceleration and braking. Braking at negative uppercase B and acceleration with uppercase A. And here we have a variable t, which basically says how much time has passed since the last time the controller has invoked. So it's a clock variable, which you already seen in the first talk. And we have under what condition this acceleration is allowed, because you need to make sure we're not going to hit the obstacle. This condition here is to capture that if we accelerate for the next epsilon time units, the system is still, the vehicle still has time to make a safe stop. So this epsilon here is the maximal control interval between two control actions. Then we use differential equation structure to model the dynamics. Distance involves according to velocity, velocity according to acceleration, time passed as constant rate, and we have this what people usually call constraint, saying the differential equation involves only when this constraint is satisfied, which means you need to do a control action at least every epsilon time units. Okay, then the safety condition we are interested in is initially we have safety, we have enough braking distance. Then after all possible executions, the system is safe. The D is positive, no matter what execution, how many executions do you have from. Okay, so that is the knowledge we have for DL. Then let's talk about relational extension. Remember that I mentioned we are going to use the biprogram structure, which in this case contains two programs of DL, the left and the right. We use the blue color to indicate host logic constructs, the red color to indicate relational constructs. This is a very simple example, which basically says +1 to your input. Okay. Then for the left and the right, left, right, both the same +1, +1. What we are saying here is we use subscripts here to say we have a projection, which we call projection, to get the value from the left execution, R to get the value of the right execution. So what this formula says is for all executions of this program, if the execution starts with the same input, it will produce the same output, which obviously holds. Here, why we say for all execution, it's because of this strange looking little thing, which is in red color. It's square brackets, which is used on the left to say for all execution of the left program. Then this one on the right is to say for all execution of the right program. So what that means is we can quantify the left and right programs in the common ways. So basically for all execution of the left program, for all execution of the right program, this property holds. The second example is a refinement relation, which as sort of the left program is a subcomponent of the right program. So the right program has two branches. The first branch is the left program. What we have here is the right program has all the possible behaviors of the left program, obviously. So the left program refines the right program to some extent. Then what we have here is for all execution of the left program, then we use another notation, which is angle bracket, to say there exists an execution of the right program, which makes this property holds. Okay, so if you read this loudly, it would be for all execution of the left program, there exists an execution of the right program that will make this property hold, which is true. Let's see more solid examples. So this is about a loop program. So this loop basically decrement the input value x until it's negative. And we have a sequential composition of two relational constructs. The first relational construct basically run the loop body continuously until it reaches the negative value. So this is a loop body for the left, loop body for the right. Then we have another relational biprogram, which says this is the condition where you terminate the loops. So we have the same program for the left and the right. This program, this formula obviously should hold, but to be able to verify this formula, what people usually need to do is rewrite it in a different way, which is something like this. You have a biprogram which basically run the loop body of the left and the right in lockstep. In this way, what you can benefit is with this relational loop using the red color, the star, to indicate this is a loop on relational structure. So this means the two loop body always run in lockstep. Then continuous run, then we can use this to identify a relational invariant which holds at the end of every loop iteration here. So using this loop relational invariant, the left equals right, for this loop body, we can verify this this probably relatively easily. Actually, this well brings to another more serious problem with relational verification, which is loop alignment. Lockstep is one particular form of loop alignment. In loop alignment, we are facing the problem of how do we align two loops when they execute so we can identify the relational invariant. In this case, we have two programs doing the same thing. Compute, which is to compute 2 times x squared. But the left program run the twice number of the iterations as the right program, because initially we have a z equals 2x for left, d equals x for only x for the right. Then this will affect how many rounds of iterations you run with the loop body. It turns out to verify this property, what you need is to have something like this, which is for every relational loop iteration, we need to run the left loop body twice and the right loop body only once to be able to identify this relational invariant 2 times y left equals y on the right. So using this relational invariant, we can verify this property, but not in the original form. We can verify this property more likely. This is a challenging problem in general for relational verification, how to find the loop alignment. And with our extension, we can rewrite the original formula into a more verifiable form, so we can use tools to really do the verification. Some more examples on CPS. So robustness, which I've been working on for quite a while. So this one is an example in the paper which talks about the control of velocity is not affected by the control of interior temperature, which should be true in general. Then here we have a by program says the left execution take one particular way of doing temperature control. The right execution take another way, control T prime. Then they do the same velocity control and run the plant for the same duration. Then if we can prove the whole formula, it means the velocity control is robust against any interference at the temperature control. We have simulation distance, which is a notion we use to do quantitative analysis. So this usually used to simulate another system's behavior from the original system. So what this says is for all executions of the compromised system, the original system is able to mimic or simulate its behavior up to a distance. The purpose of such kind of formula is to say we want to compare the behavior distance between two systems, especially the compromised system and the original system, to see how much impact the attack has made on the system. Then we have something to compare dynamics directly, which in this case, we have two exponential growth dynamics with different rates, A and B. A is greater than B, which means for all execution of the left dynamic, the right dynamic can sort of find the execution which has a smaller value, which is obviously true. But verify this formula is not as easy as you think. Okay, let's talk about verification then. Yeah. So relational verification, as I mentioned, we favor practical verification by reduce it to safety verification. The way how we do it is through a technique called self-compilation, which was mentioned by one of the talk in the morning. Similarly, the self-product. So what this technique does is basically compose two programs into one by purpose renaming and the compilation. The step we do here is in this encoding of relational formula, first is to rename the relational formula into, so the two programs have disjoint set of variables. Then we translate the relational formula into a DL formula. The subtlety, the difficulty comes in with the second step. How do you do the compilation of the biform construct? To improve the verification power, as I mentioned, we integrate different techniques to promote verification, including techniques about how to do loops and techniques for how to verify dynamics. So example, very simple encoding, we start with this formula. We rename the right program into variable y. And so we have disjoint variables for the left and right. Then we just directly translate to DL. This is very simple encoding, especially when you consider where you are here into here. What we do is what we call the sequential compilation. So you run the left program first with the for all modality of DL. Then you run the extension modality for the right afterward. This kind of a formula is difficult to verify in general. This is encoding. Most of the cases, it's kind of a trivial. This is a pi function takes the DL formula and take a relational formula, produce a DL formula. The sum of this theorem we have proved in the paper is to say our verification goal is to do this instead of the original relational formula. This one is pi function applied to renamed relational formula. This one is what I call the sequential compilation. So by program construct, we do them in sequential, which is kind of like straightforward and we face challenges. So do sequential compilation of the by program is insufficient for automated verification, which is why we integrate different techniques. The first problem we face is this one. So remember, I said you need to align the loop body twice for the left with once of the right, so we can verify this formula. And so the sequential compilation cannot do this clearly. Dynamics needs special treatment. So this one will give you for all of the left exists something of the right, which is not something easily verifiable by camera X or tools like that. What we did was to put different heuristics into the encoding, including the heuristics on loops, how we do alignment, loop alignment, and heuristics on how to verify for all exists properties, relational properties. How we do heuristics on dynamics for all exist property, and how we do actually manual inputs from the user to support for all properties on dynamics. Then we collect a bunch of benchmarks from existing work in DL and create algebra with tests. This is the result on the right saying whether we can verify it. This means we cannot. Then automated means we can verify them. Semi-automated means we can verify within 3 steps, three manual steps. Then user input automation means we can do automated verification after user input. So to cover, to summarize, we introduced a general relational extension. We did 2 encodings to reduce relational formulas to post-logic formulas. We conduct experiments on 2 case studies, and we have some proof about the expressive power of the relational extension, which is in the paper. Future work, which is not really future work, is what we are doing right now. So the automated reasoning is what we're doing at the moment. A student and I are pushing a tool to do relational reasoning by integrating different techniques. The second one is to develop ad hoc proof logic for quantitative robustness, which is something I have been pushing for the last 2 years. So thank you. Happy to take questions.
Thank you very much. Okay, I see a question over here.
Thank you. It's an excellent talk.
Thank you.
So my question is more of a, I'm trying to understand, there was one slide where you had a robustness kind of a metric row of your co-program less than B. You know which one we're talking about?
This one?
Yes, exactly. simulation distance. So that rho, right? That metric.
Mhm.
I mean, typically in robust control, I think that may be your last bullet point. We have different kinds of factual metrics, like H infinity or H2. So in this context, with its logic, what exactly is rho?
Okay, so I try to not give you all the details of technical detail, but since you're asking, so this is what we defined by ourselves basically. So it's a distance to measure. Um, it's actually it's not really new. It's something control community have been using. So it's measuring two states space, and they are different. So using Euclidean distance, for example, to measure the distance between two states, then just measure the distance between two state space. So the reason I put it here is just because I'm trying to do my agenda, because I want to push the quantitative approach of thinking in a way that everybody would be thinking about quantitatively, like how much distance between the complement system and the original system. So in this particular uh, definition, it's just the Euclidean distance between two states.
Oh, yeah, because I'm thinking in terms of control, like H infinity, H2, but that's different. That's the case.
I mean, this is just one particular case. Yeah, yeah. And I never really concerned about the definition anyway in this talk, but you can initialize it differently. Right? So.
We have other questions? I actually had one while you're on this slide. The simulation distance here, it occurred to me, having just seen the talk that came right before you, maybe this could be really useful in the context of digital twins.
I thought about that. Yeah.
Yeah.
That's a great question. And the reason I didn't ask it is because I was waiting. So that's all. So I was hoping to talk with the speaker afterwards, because essentially what they are doing is for all possible attack program, you have the mitigation program which will make the thing work, right? So that's what they're doing. So that is for all existing properties. If you think about why I have been pushing my agenda, it's because whenever I come to think about robustness and simulation distance stuff like this, everything come back to how do you verify properties like for all exists, especially in the setting of hybrid programs in the DL. So that's why I put the verification tool as my priority at the moment, because it feels like every work we have done, we need to solve this problem in a more useful way, so we can do automate verification to push the boundary. So you're totally right. We are actually able to express that sort of what they would consider probably robustness or a resistance. And this one is actually the same sort of idea. Yeah.
All right. Thank you so much. If we could have our final speaker. All right, and for our last talk in this session, we will have Anna Remke talk to us about rare event simulation for stochastic hybrid systems using symbolic importance functions. Thank you very much.
Thank you. So this is joint work with my PhD student, Matthias Nienberger, who's right now writing up his thesis, so that's me giving that talk with Karina da Silva and Arndt Hartmann from the University of Twente. Yeah, so our motivation to work with stochastic hybrid models is these are very useful models. They combine discrete, continuous, and stochastic variables. They are well suited for critical infrastructures like modeling tanks, as we've seen, power grids, charging e-cars, and stuff like that.
but unfortunately, they are very challenging to evaluate. So there's a huge body of analytical verification work, and there is a work that aims at simulation. So the problem is when we have models with very small probabilities, this requires a huge amount of simulation runs, and this is where rare event simulation comes into play. Rare event simulation is nice. It's a lot of work to actually tune the parameters, find good importance functions. And this is actually the core challenge in this work, to find a good importance function to ensure that your simulator puts the work where it can find the rare events. And this is what we tackle in this talk, finding a good importance function automatically. Yeah, so the model of choice here is a hybrid Petri net extended with general transitions. And these general transitions can be used to model random delays. And these random delays can be distributed by any continuous probability distribution. So they're not restricted to negative exponential. We have continuous and discrete places. The continuous places have this double circle, and the discrete ones, the only circle. And they correspond to the discrete and the continuous variables. And then we have transitions, and the transitions, they model the evolution of the discrete and continuous amounts. And these are continuous distributions, and you can see this tank is filled with rate 1 and it's emptied with rate 1. But only if in this control cycle you have a token enabling the transition. This is realized via these test arts. So we switch between draining and filling this tank. These guard arcs enable these transitions, and the control cycle can only go on as long as we have a token left here, right? So every time this general transition modeling a random delay fires, it consumes one of these tokens, and then we go on. And this is a deterministic transition firing after the 2. So it's a very simple model, but it still has a rare event, which I'll show you. And then for this model, we will define a property using signal temporal logic. And we will mainly use this last part. So it's an until operator. And for those who don't know it, it models the fact that you reach a state which satisfies a property specified here in this time interval, ensuring that on the way to that state, you always satisfy this one. Yeah. So if you put it true here, you have simple reachability. And we do a time bound 0 to 2 in this talk. And then we apply statistical model checking to estimate the probability that property psi holds in our model. And this property is checked in each simulation run, taking into account, of course, the specific time bound. Okay, so let's go back to this simple example. This is the property that we're interested in. So we have simple reachability, time bound is 5, and we want to know the probability to reach a state that has a tank filling of at least 4.8. So why do we want that? This is a bit difficult to see, but this property only holds if the tank is drained for less than 0.1 time. So why is that? Yeah, we fill with rate 1, we empty with rate 1, we have this time bound 5, right? And we don't want this little amount of draining because it can lead to plugging of the outgoing beds. If it's not flushed enough, then you end up having a problem. Okay, so this is our property, and then let's talk about the approach. How do we do statistical model checking for that? And actually, we use a hybrid approach, and this has been published in our recent journal paper. And what we do is we pre-compute a symbolic state space representation. It's called parametric location tree, PLT in short, and I'll explain in a second what it is. But it's symbolic in the continuous variables and in the random variables. And then we use the STL formula and put it together, and then we generate simulation runs on the PLT, making use of all the knowledge that is in there. And then we get statistical.
So the PLT is a tree structure. It consists of a finite type of locations. We have a root location, and then we go down, taking into account the things that can happen. And the location can have multiple children due to non-deterministic conflict or due to joint support of general transitions distribution. So this is the PLT for the little example I've shown you. And we have the root location up here. Time is 0 in the beginning, and the filling of the tank is also 0. Then, after 2 time units, what happens? Well, the deterministic transition fires, and this controlling token moves to the outgoing transition, right? So this happens after time 2, and because we filled the tank with rate 1, we now have an amount of 2 in the tank. So then the general transition becomes enabled, and for that we take into account the support between 0 and infinity that could be the support of the general distribution. And then 2 things can happen. So either the tank gets empty, because we drain it for too long, and that will happen after 4 time units, right? It's very easy. Even I can do it on the fly. And then the tank is empty, and we know that 2 time units have passed. So what is left from the support of the general distribution is from 2 to infinity. The other option that can happen is that the general transition actually fires, and for that we introduce this representation of S0 for the firing time of the first general transition, and the amount of fluid then depends on the value that the firing rate is, right? And this can only happen for values between 0 and 2. So now you have an idea of what this PLT actually does for you. Okay. Yeah, so now we want to do ray event simulation. And for ray event simulation, we have 2 options. One is importance sampling and one is importance splitting. Well, importance sampling actually modifies the probabilities in your model. And this is difficult for non-Markovian models. And as I said, we want to preserve this property of having non-Markovian continuous distribution. So this is not an option. Then we use importance splitting. And importance splitting actually changes the way the simulation is done. It directs the effort of the simulator into the region where the ray event is. And for that, we need an importance function. This is like the holy grail we're looking for. And it assigns the states an importance. Yeah? And these take values between 0 and a maximum of the importance function. And of course, the root will get 0, and the side 2 states that we want to reach, they will get the max of the importance. And then we partition the importances coming from the importance function into levels. So it's sort of a discretization, right? And then the idea is to spawn new simulation runs once a new importance level is reached. And we have a threshold that separates levels. And then there's 2 ways to actually do importance splitting. So you see lots of research already present in this area. And one is restart. So here we have on the x-axis the time, and on the y-axis we have the importance. And these are our thresholds. And then every restart run starts from the initial state, right? So this is one restart run, starts here, and then it reaches its threshold. And there it spawns a number of child runs. And how many does it spawn? Well, that depends on the splitting factor, FSL. And then it's -1 because the run itself is preserved. So, and such a run then ends if it crosses a threshold from above to below. This is important, its own creation level, right? So this here is the original run, which is created here. So it is allowed to cross from above to below this threshold. But this one is newly spawned here. So it ends once it tries to cross this threshold from above to below. It also ends if it reaches a state that violates our property. Yeah? So these are marked with an X. And it also ends if it reaches a precise 2 state, which is actually our desired rare event. And this is with this check. So this is what goes on in restart, and it results in this function. It's n divided by the product over the importance levels of the splitting factor, given that n runs actually reach side 2. Yeah. So this is restart, and you can see how it spawns these new runs until it finds this way. The other option is fixed effort, and this is a little different because it consists of a number of partial runs on each level, and the number is given by Fe, and E is the effort function. So you can see, in difference to restart, we have a number of runs starting here, and how many? Well, that's exactly Fe. Yeah, and then you go on, and once you reach a threshold, this run is actually stopped. So these dots have a different meaning now. And then for all these dots, we spawn partial runs, and in total, as many as the effort function tells us. Yeah, and this is done here again. And then a run ends if it crosses a threshold from below into the next level. Yeah, this is these dots. Or again, of course, if it finds a gray event, or if it finds the violating state. And the result of fixed effort is then given by this, again, the product over the importance levels. And this is the conditional probability to reach the next level, given that you are already here. So these are two slightly different ways to direct the simulation into the correct direction. Well, you've seen that we need many parameters still. Yeah, even if we have the importance function, we need these thresholds, we need the effort function, and we need the fitting function. For that, my colleague Arne Cartmans, together with Carlos and Pedro, they have proposed expected success. And this is a method to determine levels and splitting factors fully automatically, and it's based on the balanced growth rule, which states that on average, one run actually reaches the next level, the others die. And expected success uses fixed effort pilot runs with a certain parameterization until it finds at least one gray event. And then it iterates over the importances I, and it creates a new level at threshold I+1 and the corresponding splitting factor for restart. So it gives you automatically the parameters you need for the restart function. If you want to use it for fixed effort, the user is required to specify a base effort E, which you can multiply with the splitting factor, and then you have your effort function. So this is the work we built on, and we want to apply this to the simulation on the PLT. So we extended the labeling function that we presented in that journal paper to use for ray-event simulation. And yeah, what we did is we introduced these two sets of labels. And just to give you a quick idea, these labels will be added to the locations in the PLT, telling you whether the property of interest is satisfied, then you get a top, or whether it cannot be satisfied, then you get a bottom, or whether we cannot decide, then you get a question mark. And these tuples we need for the until operator to say whether the first part of the until property is satisfied and whether the second part of the property is satisfied. Yeah, and then LP holds all labels where the property of interest holds for at least some states of the application. Now recall, we are in the hybrid domain. So I have like an uncountable number of states in my location. And then we have LU, and those are the labels for where we cannot yet decide the validity of the package. And that is enough to build the symbolic importance function on. But let me just quickly give you an idea. This is the PLT, and here we have the labels. They are introduced here, and you can see that the green location here is the only one satisfying our property, and this one immediately violates it. So we don't need that one. And for the others, we are orange because we need to pursue the simulation. Yeah, and one other important thing is we have to take a look at where we need to sample. Yeah, whenever you general transition fires, we need a new sample, and this is of course very important information for the importance function. So we have this little beta, and if beta is 1, we need to sample. If beta is 0, we don't need to sample. So then we can proceed and request for the importance function, and it's based on the labeled and reduced PLT. I have not been talking about the reduction of the PLT. Time is limited, and the beta indicating whether sampling is required. Yeah, and then we add labels to these locations. Sorry, we extend the locations with importance based on labels. So we add the importance. And if we have the label bottom, then we need a low importance, yeah, as the corresponding state to the level of the probe side. If we are in LP, recall P is the partially filled, we'll have a high importance. And if we are in undecided, then we need to compute the minimum distance to the location, the next location, with a label from LP. Okay, so we need a distance function. And the distance function is defined for the PLT. V is the set of all locations, and this is my root location. I remember the one on the top. And then we recursively define the distance for every location. And it's 0, well, if we are partially satisfied, then we are 0, right? If it's infinity, if we are in bottom, then it cannot be fulfilled anymore. And otherwise, if we are undecided, we have this recursion, and we compute the minimum over all children, and we add the distance of child I plus an indicator function for that child I. And the indicator function does the actual work because it adds 1 if this location has a label in LP, or if it needs sampling, right? So here, this is the one location that fulfills the array event. Then we have distance 0, and then the distance grows here to 1 because we need to take the distance of this child plus the indicator function, which is 1 because this child has a label in LP. And this is done to ensure that the distance actually grows when you move away from this fulfilling location. And then here the distance again grows, but it grows because this child has beta is 1, so we need sampling. And then here we actually have to compute the minimum, and that is easy, delta 2. Distance doesn't grow because here beta is 0, and this child is not an LP. And then here again, distance grows because beta is 1. So we increase the distance for the sampling, and once we move away from the LP location. Okay, so that allows us to define the symbolic importance function based on the distance function. And here it is. Now it seems really easy, but we've done a lot of work until here. So it actually takes the maximum of 0 and the distance between, we subtract from the distance of the root location, the distance of that current location. So with that symbolic importance function, we can take a look at the running example, and we compute the 95% confidence intervals around the midpoint for this property psi after 10 minutes of simulation time. So after 10 minutes of simulation time, we cut off. Either we didn't find a rare event or we did, then we're interested in the size of the confidence interval. The smaller the confidence interval, the better our result is. And this symbolic importance function, we use once for splitting factors and effort functions determined by this expected success, which I just explained, and once manually determined and tuned. This is what the simulation people actually do. They like playing around and tuning their parameters. Yeah, okay. So these are the results. And what we have up here is the time that we need for the pre-compute. For this little example, it's negligible as 0. And then we have the 4 versions: fixed effort, a manual, expected success, same for restart. And here we have the simulation we proposed recently in our paper. And then we scale the number of control tokens. Yeah, we call the general transition can only fire if there's a token left in this control phase. And of course, the more tokens we have, the larger the model gets. This is still a small example. But what is very interesting is that the original method can only find the events for 4 tokens. For 6 or 8, it's not able to find it in 10 minutes, yeah. And then fixed effort and restart in the manual configuration, they actually perform best. And if we combine them with expected success, they are in most cases still able to find the event, but they require more simulation time. And it appears that a restart seems to be a bit more robust against expected successes, not optimal thresholds. Yeah, so what you can see is ray event simulation is really needed here. Our symbolic importance function does a great job, but expected success is not yet completely up for the job, I would say. Yeah, that's what I just said. And in the paper, we have 2 bigger case studies where actually the pre-computations take time, but not too much time, so it's still all very doable. And the approach performs very nicely, but also in the larger models, you can see that expected success only works in certain cases. And we think that this expected success method requires that the effect of specific samples manifest soon enough. So if there's too many things going on in between, it's not able to keep up. So this is where we want to direct our effort into future work to actually improve expected success, to work in all cases and have a fully automated overall approach in all cases. So thank you very much.
Thank you. Right, do we have questions for our speaker? I will start. This is fascinating. And I was thinking the whole time, though, that your results critically depend on the input STL formulas, right? That they represent exactly what you think they do, that they accomplish what you want. And STL, you know, there have been fun papers, things like this, right? So I was wondering if you could tell us a bit more about how you derive the STL formulas and how you validate them so that you have that confidence that you could carry through as you're analyzing them in this.
Yes, of course. So the example STL formula was a bit tricky. Yes, yeah. But once you write it down, it has a syntax semantics, which you can check on one simulation run. So to check this reachability on every simulation, and this is perfectly feasible in all our models at least. Maybe the difficulties come into play when the continuous evolution is more difficult. So here it's all piecewise deterministic. Yeah. I think if it's still linear, it's also doable, but once it gets non-linear, you'll have ambiguity.
But essentially, it's like an interactive process with your simulation of essentially simulating your. Okay.
No. The creating the STL formula.
Yeah.
No. Normally, you get your requirement.
Yeah.
You get your model. And
Okay.
Yeah. So you define your safety property.
Yeah.
And you make sure that you don't violate it. Yeah.
Thank you.
You're welcome.
Do we have any other questions before we close the session? All right, with that, thank you so much.
Thank you.
Thank you for staying for the last session of the day. I hope you had your fair dose of caffeine. Let's get started with the first talk of the session.
Andrea Bobarda will present to us how they're able to eliminate flakiness from non-deterministic specifications. The floor is yours.
Thank you so much for the introduction. So welcome everyone. I'm Andrea Bombarda from the University of Bergamo in Italy. And this talk is about eliminating flakiness, a deterministic control for validating non-deterministic meta specification. This is a joint work together with Silvia Bonfanti, Angelo Gargantini, and Nico Pellegrinelli. All of them are from the University of Bergamo, as me. So during this talk, I will first introduce the problem of test flakiness. And I will explain how we can have a flaky test even with the meta framework, which is a framework that we have been developing during the year for abstract machines. And I will explain a little bit about the framework as well. I will talk about the coffee vending machine case study, that is the running case study that we use in our paper. And then I will explain why it is non-deterministic and how we can solve this problem. And then I will end my talk by giving a very simple evaluation and by discussing future work and conclusion. So in software engineering, we know that a flaky test is a test that sometimes fails and sometimes not. So basically, it changes the outcome without any change into the program code. And there may be several reasons for which a test can be flaky. Basically, we can have some problem in race condition or concurrency. So you may have different processes that can access to the same resources. So sometimes a process find the resource free and sometimes not. So the test can fail for this reason. Then we may have some dependency on external systems, such as we are accessing to databases or APIs. And it can happen that while we are executing the test, the service that is offering the API is down. And so we are not able to reach it. And so we have a failure. We may have some problem related to time-based logic. So you know that if you use a sleep in a test, then you cannot be sure about the exact duration of the sleep. And the same for the timeout. And lastly, we may have some randomness or non-deterministic behavior. So just to give you an example, suppose that if you have a system that you want to test, and in this system, you have a process that tries to roll a dice. So when you roll a dice, then you may have different runs. So one run can have the outcome equal to 1, one other run can have outcome equal to 2. And so we want to write some test cases to test this program. So you may have the test 1 that checks whether the result of the roll a dice procedure is 1, and another test that checks that the result is 2. So if you try to execute these two test cases and you have the different runs, what you can have is that in the first case, so if you have the outcome equal to 1, you will have the test 1 that is passing and test 2 that is failing. And in the second test, in the second run, you may have test 1 that is failing and test 2 that is passing. So what we say is that these two tests are actually flaky tests. So, okay. Which is the problem of test flakiness? We know that having flaky tests influence the trust that tests have in their test suite. So this is something that we don't want to have, especially when dealing with complex or critical systems. We know that they can mask real bugs. So basically, they reduce the software quality. And they also lead to wasted time because we are trying to diagnose something that is actually not a real bug, but is false positive. And the main problem that we want to address is that basically they can occur even when testing formal specification. And you know that normally what we do is working with formal methods, formal specification, because they have some kind of mathematical guarantees, so we can prove properties. But if there is something that is not deterministic and we are not able even to run tests on this specification, this can be a problem that can affect the trust that we have in this specification. So in our work, we deal with ASMETA specification, and I will explain you what ASMETA is. So ASMETA framework is this very complex framework. You can access to the GitHub repository in which you can find the tool by scanning the QR code. Basically, the ASMETA framework is a framework that supports the development of abstract machines. So you can start by modeling your specification as an abstract machine. You can try to validate it by using some scenarios, or in general, you can think about scenarios as test cases. You can perform even some verification activity by using a model checker, and you can generate automatically the executable code in the test case. So these are all the activities that are supported. And in this work, what we did was extending the validator and extending in particular the modeling language that we use to write the test cases for the meta specifications. So I said that we are dealing with abstract state machines. Abstract state machines are an extension of finite state machines in which basically we are extending two different things. The first thing that we are extending are the states. So states can contain arbitrarily complex data, such as the numerical functions. But we are also extending transition rules. So we are extending how we pass from one state to the other. You can see below that there is an illustration. So we have different states, S0, S1, S2. And while we pass from one state to the other one, we have the execution of the abstract state machine, so a run. And one state is can be considered as the configuration of the system and the environment. And then we have two different notions that are the monitor functions and control function. So they are more or less equivalent to input and output. So you can see that monitor function is something that is modified by the environment and read by the system, while control function is again modified by the system and possibly read by the environment. And while we are executing these runs, basically we are applying some kind of state transition. So we apply all the transition rules that we define in our abstract state machine so that we can pass from one state to the following state. So this is an example of our running case study, the coffee vending machine case study. You can see that basically we are defining a set of domains, a domain like domain product that can contain coffee, tea, and milk. We are defining a control function. So this is kind of an output, and we are deciding which is the dispensed product. And then we have some rules. In this case, we have only one rule, that is the main rule. You can think it about like the main method in classical programming languages. So it's the entry point that starts the execution of each step of the state machine. And here in the main rule, what we are doing is choosing one element in the domain product and then dispense this element. So of course, this is a very simple specification, and we can write also a more complex one like this one, in which we basically are introducing also a subset of an integer domain, that is the point domain. And so instead of dispensing a product totally randomly, what we do is consider also the price of a product, so that you ask you ask the user to insert some coin, and then you dispense only the product that actually met the condition to cost less than the number of coins inserted by the user. So in both this specification, what you can see is that we have this choose rule. So this choose rule is what we are using to implement non-determinism. So we are choosing an element in a domain. So I told you that the choose rule is not determinism, but actually as meta supports two different kind of non-determinism. The first one is what we call the external non-determinism. So these are basically the monitor functions that are read from the environment to make choices. We can consider them as not deterministic because while you are writing a specification, you don't know a priori which is the value that the user will insert. So it's more or less something that is not deterministic from the point of view of the developer. But actually, the thing that we consider the most is the internal non determinism. So we are using some kind of algorithms to make choices, and this is what we are considering in this paper. So this internal non-determinism is implemented by this choose rule. So you can see we want to choose an element D in a domain D with a certain condition. So this is a guard. So we want to extract only the elements that satisfy the guard. And then for the element that has been extracted, we execute a rule that can be an update rule, a transition rule, or whatever. And if there is no element that satisfies the condition, then we execute like a backup rule, what we indicate here with Rn. So this is what we deal with in our paper. And in particular, we want to deal with non-determinism with the scenarios. So these scenarios are like abstract test cases that we can write. And with these scenarios, what we are doing is basically setting the values of input. So the monitor function, as you can see here, we are setting that we are inserting a single coin. Then we can do some steps. So we make the ASM proceed one or more steps. And then we check the values of the controller function, so the output or the internal state of our system. So this scenario is, I would say, very simple. It has two different steps. You can see here, step 1 and step 2. And in particular, we have two different behaviors. So in the first case, we are inserting only a single coin. And when you insert a single coin, the upper state machine has been implemented to deliver only milk, because milk is the only product that costs one single coin. So even if the choice of the product is done randomly, at the end, the behavior will be deterministic, because the only product that will satisfy the guard will be the milk. So this is OK, and we like this kind of scenarios. And these checks will basically succeed. So this part is actually deterministic. The problem comes from the second part. You can see that we are inserting two different coins, and the state machines have been implemented to choose between coffee and tea with 2 coins. And in this case, what we are doing is insert 2 coins, then we make the state machine to proceed 1 step, and then we check whether the product that has been dispensed is coffee. So this part is actually non-deterministic, because since we can choose between coffee and tea, we don't know a priori which will be the choice that will be done by the coffee vending machine. So since these scenarios are what we call tests, we can say that instead of speaking about test flakiness, these can be scenario flakiness. So sorry for this problem, it's like a visualization problem. The bar should be about test and not about flakiness. So why this scenario is flaky? Because you can see here, this is a successful execution. You can see that actually the choose rule choose the coffee as the dispenser product. So all the checks succeed. While in a different execution, you can see that the state machine choose T, and so we have some check that is failing. So this is something that is not deterministic, and it's something that we would like to avoid in our scenarios. So what we did was extending this language that we use to express scenarios, so test cases for abstract state machines, by introducing an additional statement. So you can see here that the problem is only in this second step, because it is the same scenario that we analyzed before. And the problem here is that when we insert 2 coins, we don't know which will be the choice made by the coffee vending machine. So what we did was actually introducing a new statement that we call P. And with this statement, we specify which is the value that should be chosen by the abstract state machine, by the simulation of the abstract state machine. So if you see here, this is our main rule that we are trying to test. And in this case, we are choosing an element P in the domain product. And this choose rule is inside our main rule. So in this pick, what we do is to say that we want to pick the element P that is specified into the main rule, and this should be copied. So that in this case, what we are saying is that even if the specification is not deterministic, while you are executing this test case, the specification should behave as a deterministic specification, because we are forcing the value that should be chosen. And the advantage of this is that all the execution of these scenarios will choose coffee as a product during this choose rule. And so the scenario will be actually deterministic. Now, we call this a deterministic control over non-determinism, because the specification will remain non-deterministic, but we are somehow controlling its behavior. So this is how we define our pick statement. So we pick a value in a rule name, and then we assign its value. So the rule name is, of course, optional, because you may have a single choose in your specification. And so it is not important to specify the name in which the choose was. In our case, we used it as well. So actually, what happened in background is that when you write an Avala scenario, the validator automatically translates it into an Asmeta model. And so the idea was, how can we do this translation without affecting all the other possible implementations? So if you don't want to use the pick statement, how can we implement this new statement without changing the execution of all the scenarios that are not using actually a peak. So, of course, scenarios that do not have the peak should be treated as before. This is something that we wanted to obtain. We know that scenarios could have only peak in some steps. So you may want to transform some step to be deterministic and some other step to be not deterministic. And the other thing should be that only valid values must be picked, because remember that in the choose rule, you can specify a guard and only the elements that actually satisfy the guard can be picked. So we wanted to assure this thing. And so what we did was implementing a translation like this one. So you can see this one is our scenario. And in this step, we are picking an element. So we are picking the value t for the parameter p. This scenario is executed against this meta specification. And so while we are trying to execute a scenario, this specification is translated in a new specification in which we do some kind of modification. So basically, you can see that we add two new functions. So one function that says whether we are actually picking or not the value for the specific step. And the other is basically storing the value that we are picking if some value is. Then at the beginning, we say, OK, we are not picking any value. And then while executing the main rule for each step, if the value is picked, then we set it to true, and we set the value that we picked in the scenario. Otherwise, these two statements will basically not exist. And so the execution will be as normal. So you can see that here, so that there is things above, but you can see that we have some check. So you may have the regular behavior, well, if you are not specifying the pick statement. You may have this one that is the behavior that is used when you specify the pick statement. And then there is the third one that is like a check failed that specifies that the value could not be picked, whether if the value was clashing with the guard that was set in the code. So what we did was conducted a preliminary evaluation of our approach, and we tried to address the problem of collective scenarios with 3 different techniques. So the first technique that we define is a technique that we call classic technique. So the scenario is, OK, you want to avoid having some kind of flaky test. So what you do is writing scenarios in a way that they can never fail that. So if you have like a check statement that should check the result of an operation that can change between 3 different values for non-deterministic reason, what you do is to write a check that is actually checking the OR between all possible values. This is something that is not very effective, and we will analyze why later. Then there is a second approach that we call the flaky approach. So in this case, we are writing scenarios as usual. So sometimes they can fail, sometimes they cannot. And then there is the third method, that is the peak method, in which we exploit this new statement in order to avoid flakiness, and we check whether they are effective or not. So just to evaluate, I want to exploit a very simple choose rule. So this is a choose rule which tries to extract an element P from the domain product. So this is the original version. And now suppose that this choose rule is implemented in the wrong way. So instead of picking a value, choosing a value in the domain product, what you do is that you choose the value in a subset of the domain product that is tea and coffee. So basically, this choose rule could not dispense milk. So we can have the 3 different approaches. The first one is the one that is the classic way. So basically, what you do is you don't want the test to fail, and so you write a check that is composed by the OR of 3 different checks. So in this case, you are checking that the coffee vending machine is able to dispense tea or coffee or milk. And this will, of course, succeed. So you won't have any failure in execution of this test case. But this is something that we don't want, because we are actually missing the fact that there has been an implementation error. And then there is the second approach, the flaky approach. So let's suppose that you write step check dispensed equal T. And so in this case, you will have that the the test sometimes fails and sometimes not. The problem is that even in this case, we don't know whether the test is failing because T is something that we are not choosing from, or because there is some non-deterministic reason behind these failures. So what we do is using this pick statement. So you can see here that we want to pick an element P in our main rule, and we choose the element milk. Then we try to do a step, and then we check whether the dispense is equal to milk. And at the end, when you try to execute in this scenario, you will have a failure. So yeah, in Teams, but there is an X, a red X below. The problem is that in this case, you will have an error that says that milk cannot be picked. And so you are able to identify that the problem was not in, for example, in what you're doing here. So dispense equal P, so this was correct. But the problem was that here, so P could not be milk because there has been an implementation error. So let's analyze a second error. So in this case, what we are doing is changing again our choose rule. So this is the original version. Here, the domain is correct. So we are using a still product. But what we are changing is the behavior. So you can see here that instead of dispensing the product that has been chosen, actually what we are doing is dispensing something else. So if we choose milk, we dispense coffee. Otherwise, we dispense the correct product. So if we choose P, if we choose T, we dispense T. If we choose coffee, we dispense coffee. So again, let's analyze the three different approaches. The first one is the classic approach, in which we do the OR of all the possible products. And in this case, again, this scenario will never fail, because at the end, no matter which is the product that is chosen in this domain, the output should be or coffee or tea or milk. So this check will never fail. And then we have the second approach. This is the flaky approach. So in this case, we are checking whether we are dispensing coffee. And again, sometimes these will fail, but not because there is an implementation error here, but maybe because the product that has been chosen was tea and not coffee. And sometimes instead, it doesn't fail. But again, when it doesn't fail, we don't know whether we are executing this part of the code or this part of the code. So we are not able to identify the problem. And so again, we come to the pick way. In the pick way, what we are doing is we set the element that should be chosen. In this way, we can set milk, and then we check the output that should be again milk. And in this case, we are able actually to identify the problem. So we will have a failure in the execution of this scenario. And the problem is actually very easy to define, because at the end, since we are setting milk, we know that we are executing this part of our meta specification. And so the problem is that actually we are dispensing something that is different from what was chosen before. So these, of course, increase our fault detection capability. So just to give a summary of the three different approaches, we have the classic approach, the flaky approach, and the pick approach. And both of them, all of them have some pros and cons. Basically, the idea is that if you use the pick approach, then of course you need to learn new commands, you need to control non-determinism in an explicit way, and of course you need to write multiple scenarios, because since you are forcing the values that are chosen by the choose statement, then you need to write multiple scenarios, choosing every time a different value. But in this case, with the pick statement, what we can do is that when some failure occurs, then the cause is very clear. So we have an enhanced fault detection capability. But instead, with the classic effective approach, we have every time that if there is a failure, that the failure is the causes of this failure are not clear, and sometimes the identification of the failure is even impossible, because if you write with the classic way a check that checks the OR of all the conditions, that then this will never fail. So this was what we did. Some kind of future work that we are working on are basically the use of pick statements when multiple values are chosen. So in the choose statement, actually what you can do is to choose one value in a domain D1, another value in a domain D2, so something like this. We are actually dealing only in the case while you are extracting one value from one domain. So this should be an extension we are working on. And then, since with the meta framework, we are able to automatically generate scenarios from a specification, we want to include this pick statement also doing this in the scenario generation so that we avoid the generation of flaky scenarios. And at the end, we want also to perform some kind of quantitative impact of this big statement on more complex specifications. So concluding, I have explained why flaky tests are a problem in software engineering, and these are problems also when validating formal specification. We introduced the concept of flaky scenarios instead of the regular flaky tests that are used, that are common in software engineering, and also a method to control internal non-determinism. And at the end, we discussed pros and cons with a simple copy vending machine case study. And we discussed also how, with our solution, we can improve the full detection of our test case. Yeah, this concludes my talk. Thank you very much. And if you have questions, feel free to ask. Thank you.
Do we have any questions from the audience? Okay. So I was wondering about the classic approach. When considering that the domains may be finite, what it seems to be the case here, we could also potentially apply MCDC to cover, the flakiness for the people that prefer the classic approach, right? Is that something?
Yes, you can do it. The problem is that sometimes the state space explodes because it can happen that you are not checking a single value, but you're checking a combination of values. So it can be more complex to do this, but you can do it.
Actually, I have another question. Is there any benefit to allowing users to prepare their own, a specific case, like preparing the classic approach or even the flaky approach? Is there any reason why, you want the users to still consider those cases?
Yeah, I mean, if you are dealing with non-deterministic specification, then probably using this big statement is the better option. But of course, we didn't want to force user to use only the big statement if there is non-determinism in the specification, because maybe the user do not know that there is a non-determinism, internal non-determinism. So we wanted to allow them to use all the specific possibilities.
Does Meta provide means to provide like is that something that
no. We have an idea to include the probabilistic ASMs, but we are not at the moment. They are not supported.
Hey, great talk, Andrea. I was wondering if you have tried to apply this technique to maybe a real system, or how well does it scale to more complex exams?
No, we only performed the preliminary evaluation, the one that I presented here. But it's something that we definitely want to do to apply this to a more complex system to see which is the impact also in terms of fraud detection.
Okay, since there are no more questions, let's send the speaker again.
Thank you.
And head to the second talk of the session. Edward King will be presenting their work on sim to real problems. Is that right? The floor is yours.
Hi, everyone. Sorry for the. My name is Edward Kim. I'm a postdoc from the Electrical Engineering and Computer Science Department at UC Berkeley, advised by Professor Sanjay Secha. And today I'll cover a topic on querying label time series data with scenario programs for sim to real validation. So let me start off with providing some context. Simulation has been widely adopted almost as a standard practice to test cyber physical systems across domains. For example, self-driving, manufacture, healthcare, and there are simulators that are almost like a digital twin of the environments that they're operating in. And why are people using simulations? Because simulations are safe, no one's going to get injured during this testing, and it's scalable, meaning you can run hundreds of simulations in parallel. And as a researcher, I've been developing tools to support other developers to extensively and rigorously test system properties in simulation. However, one day it occurred to me that is what I'm doing really practical. Are failure scenarios that I identified in simulation actually reproducible in reality? And the reason I had this skepticism is, I mean, I can obviously see the difference between like these RGB data, and I wondered, okay, if we're testing with synthetic data, these systems, how would the behavior differ if I use the real data and test them in real life? And with that, and therefore the failures that I found in simulations, do they actually reproduce? So this is like a sensor realism issue right here. So what do people do to actually validate this sim to real reproducibility, which I call sim to real validation problem? For example, in autonomous driving, people do track testing. So they go out. So in our case, we created in collaboration with AAA insurance company. We went out to their track testing site and tried to find a failure scenarios in simulation for their autonomous car, and then try to reconstruct that scenario in real life and see if we can reproduce that. And after spending days on the track testing site, we were able to replicate some of the issues that we saw in simulation. Like right now, the car is running over a pedestrian. But what I got out of this experience is that this is very inefficient. It requires a lot of physical labor to reconstruct each scenario, and therefore this is not going to be a scalable approach. So that was a source of agony for me for years. And then 2 years after, we proposed the following idea, in which this work is an extension of, which is okay. Once we identify failure scenarios in simulation, we can encode them more formally as a scenario program, which I will go over soon. And then as we see a trend nowadays that across academia industry, folks are collecting massive amounts of data and they're also labeling them. So suppose we have a labeled real world data set. Can we find a matching subset of the real sensor data from that data set? If we can do that, then we can use those data to test whatever machine learning model that was failing in the first place, whether it's perception, behavior prediction, or planning. Therefore, we can do this sim to real validation in a data-driven way. And the aim of our work here, so back then this was only for static images. Now the question is, can we extend this work to the time series data so we can actually generalize this approach for tasks that involve time series like planning and behavior prediction and so on. So the contribution of this work is the following: a novel problem formulation of querying a labeled time series data against a formal scenario model, a sound query algorithm which can be used to validate candidate failure scenarios for different ML models, and experiments demonstrating that the algorithm is correct in practice and also scalable. Outline of the talk is the following, which is cover related work, problem definition, methodology, followed by the experiment. So for the related work, there are two major branches approaches taking place. One is in the database system. And so in this approach query is very fast. However, the expressivity is very low. So when I say expressivity is low, it's things like you cannot express physical interactions or dynamic interactions between objects. It's more like, get me all the scenarios, get me all the videos or time series data that involve a red car at an intersection. That kind of limited expressibility. Whereas vision language models, you can high expressivity, you can express in natural language. But the query time, the time it takes to query is slow, and there is no guarantee of correctness. So the goal of our work is, can we bring the benefits of the both world? So keep the high expressivity, fast query time while guaranteeing correctness. But before we get into the problem, formalize the problem, let's cover some background. So what is the scenario program that we're going to be using? So in the group that I'm in, we developed a scenario modeling language called CNIC, which is a probabilistic programming language. And over here right now, on the right side is a snippet of a CNIC program showing modeling the scenario on the left side where a car is going straight and has to change the lane because of a stationary car in front. So in this case, so over here you see ego defined is a car on road. That means uniformly randomly on road. And then the other car is on ego's lane that is visible to ego. And then there's a behavior assigned. And for ego's behavior, there's a distribution assigned here where ego will by default follow lane, but will be interrupted by another behavior when the ego's distance to another car is within a uniform random distribution of 1 to 15 meters. Right? And so the input to the scenic program are the state of the world, positions, orientations, and so on of the objects. Output is the actions for each object, like follow lane, lane change, stationary, and so on. So a scenic program models a distribution of labeled traces, which I'll define next. But these are traces of inputs and outputs. And so what is a label trace? Label trace is a sequence of labels of each sensor frame. And a label is a concrete values of semantic attributes. So for example, a snapshot, first frame here, shot from a visualized from top-down view, includes things like, okay, what is object ID? What is a class type? Position, orientation, which lane is that object on? What action is that object taking? So for example, object ID 1 is a car at a specific coordinate with a certain radians, and it's on lane 1, and it's just following lane, and so on. This is what I mean by label. And it includes, in the previous slide, what it means by the input, which is the state of the world, and then the output, which is these actions. So the problem formal definition is the following, which is given a label trace L, a scenic program P, and a positive integer M. First of all, find an object correspondence between the objects in the scenic program and the objects in the label trace. So right now, in order to reason about this scenario that I just covered, we need to know, okay, which car is ego car in this video, and then which car is the other car. So, and that correspondence is unknown. So we need to search for that correspondence. And then if that correspondence exists, then we need to also look for M-length segment, sigma M, of the label trace. So what is this M-length business? Well, basically we want to query, does the video contain the scenario? So you may have other scenarios that are not specified in the scenic program. But as long as it contains that content of the scenario for certain duration of time, then we want to accept it as a match data. So this M is basically giving you that parameter as to, okay, given a 40-second video, as long as it contains 20 seconds of scenario content matching the descriptions in the scenario, give that to me as a matching behavior. So that's what this M parameter is about. And then what is this TP? So TP is a set of all the traces that is in the support of the scenic program. So as I mentioned before, a scenic program is representing a distribution of label traces. Now we're looking at the support of it. So the methodology is quite straightforward. It's divided into two steps. First is object correspondence. So we're going to look for all possible object correspondence, select one feasible candidate, and then do a scenario matching, which scenario matching as in, okay, is each object that we found a correspondence, are they doing the behaviors as specified in the program? And if not, then we go back, take another feasible object correspondence, and then go back to checking the temporal aspect of the query. If not, go back until either we find a matching object correspondence with the temporal matching that are temporally matching, or at which point we output true. Otherwise, we exhaust all possible object correspondence, and then at which point we output false. So let's start off with object correspondence search. So in the scenic program, that as a running example that we're using, there are two objects, ego and the other car. And then the objects in the label trace, for example, as you saw in that video, there were a lot of cars, some pedestrian, cone on the side. So there are a lot more objects there. So there are potential ego, and right now ego is a car, the class type of the car. So is the other car. So possible candidate for ego are all the objects that are car. So is the other car. So let's select one possible candidate. So ego can be a car 1, other car would be car 3. Let's try this one out. And then now we want to check given this correspondence, we want to check the rest of the scenario, the temporal aspect, which are the behaviors. So for the behavior, we will convert, first of all, formally represent the behaviors of each object as hierarchical finite state machine, where it's a syntax-driven compilation of the program into this finite state machine. So at the top, there is a ego behavior, and inside the ego behavior, we see follow line by default. So it's the initial state there. And then when this interrupt condition, which is this guard, is satisfied, we'll transition to a lane change. Otherwise, if not, then we'll switch back to follow lane, following the semantics of the scenic language. And by default, it's self-looping until any of the transition conditions are satisfied. And then so is for the other car behavior, which is just stationary. So we would start at a stationary state and then self-loop. And then the output of this finite state machine is, in this case, basically the action that each behavior is taking at that point. So let's do an example of scenario match query. So first of all, here's a different snapshots. So this is the visualization of the sequence of label trees. So at time t0, there's a blue car, which is an ego car at this point. And the labels on top of it, FL is a follow lane, ST means stationary, LC means lane change. So these are the actions that are being taken by each object. So at the beginning, there's a ego car, which is a blue car, following lane, doing lane change, and then follow lane again. Then realize, there's a stationary car in front, and it's taking a lane change again. So if you compared, so at the beginning, we should check first that the initial scene are matching. So over here in the green box up below, ego is a car anywhere on the road, and then the other car is on the ego lane that is visible to ego, according to the syntax and the semantics of scenic language. And according to this description, the first two are not matching the scenario description because ego car, the other car is not on the ego's lane. So we move on to the third time step, and over here, at this point, ego and the stationary car is on the same lane. So here the initial scene is checked to be correct. And then at this point, we check, okay, what is the guard condition? So we look at the distance, and distance is 14. And at this point, according to the semantics of the scenic program, the range, as long as the distance is within the range of 1 to 15 meters, and the value can be sampled from 1 to 15, in this case, it can be either true or false. So it can be true when the value sampled from 1 to 15 is, let's say, 15. then 14 would be this guard condition would consider to be true. If it's sampled to be 13, then it will be false. So in this case, because of this distributional aspect, both true and false can be satisfied at the same time, creating a non-deterministic transitions. So in this case, for the second one, the third one, fourth one, and fifth one, it's all matching the scenario description. So if the m value that you initially provided is a 4 or less, then this query would be returning this label trace to be matching. Otherwise, if the m was longer than 4, it would be false, and then it will go back to the finding the other object correspondence and then checking for the scenario match query again. The support a scenic fragment for this match query, right now it allows any sequential and interrupt-driven behaviors, but it does not allow variable assignments. So we're only supporting memoryless behaviors at this point. And for the sake of time, I wouldn't go into the proof, but we provide a theorem that given a scenic program, a label trace M, our algorithm outputs true if and only if the label trace matches the scenic program, the program for a window of length M. Otherwise, algorithm outputs. So now moving on to the experiment, we try to validate two hypotheses. So how is the correctness of the algorithm in practice? And does the algorithm scale with respect to the complexity of the program, which I will define soon. So regarding the correctness, the accuracy, we use nuisance data, which provides labels for, in this case, 400 different RGB videos. And they were all duration of 40 time steps, which equivalent to 20 seconds. And then we came up with 4 different interesting scenarios. And then we compared our algorithm against the benchmark, which in this case was the vision language models. For example, Claude 3.5 and GPT-4o, which were the latest models at the time of this experiment. So to the vision language models, we provide scenario descriptions in natural language, labeled video, and then the LLM prompt. And then likewise for our query algorithm, we provided the scenic program, labeled video, and M of 20. So in the LLM prompt that we provided to the LLM, we're giving the same specification as we're giving to the query algorithm, but in natural language. So we provided 4 different scenarios. First one is the one that you just saw in the video. For the time's sake, I'll just skip over the scenarios. But we checked. We were checking against 4 different scenarios, and then this is the accuracy result. So on the left, the first column on the left is showing different scenario numbers. Each column is showing different benchmarks. So the first one is Claude 3.5, second GPT-4o, and then the third algorithm, and it's showing the accuracy number. So if it's 1 is a max. It means it correctly identified all the, it correctly queried all the labels of videos correctly. If it's 0, it's a worse performance. And our results show that on average, our algorithm is performing the highest, about 0.8 with plus minus standard deviation of 0.2. And also in terms of the average runtime, it's magnitudes of orders of magnitudes faster. So, but before we get in there, we do see some errors with our in the result. And upon analyzing, we identify that the errors were in the label trace. Some of the attribute concrete values that the semantic attributes in the label contained errors that resulted in this inaccurate report query. So you may find, so the key takeaway is the following, which is that by making use of the existing label data, we can query up to 3 orders of magnitude faster with higher accuracy. And you may say this is a unfair comparison because LLM is taking the video while the our algorithm is taking the label trace instead. So that's why you may have difference in terms of the query time. But I think that is exactly the point that we want to make, that these label data are already out there. We're putting massive amount of time and effort to collect those data and are even open source. So by making use of the existing data, we can query up to 3 orders of magnitude faster with higher accuracy. Next one is a scalability experiment, and with respect to the complexity of the program. And when I say complexity, it means with respect to either time or the number of objects. And for this one, we selected one of the scenic programs that we used for the first experiment, and then scaled and then generated labels using the scenic program in simulation. So this was synthetic label data. And we generated with respect to time and objects. So here on the left plot shows scaling on the x-axis with respect to time steps from 20 to all the way to 100 time steps. The y-axis is showing average query execution time, which is in milliseconds. The second plot is showing the number of objects on the x-axis. Y is execution, the query time in seconds. So it shows that the number of time, the query time is scaling almost linearly with respect to the number of time steps. And then with respect to the number of objects, it's growing exponentially, and particularly because of the combinatorial matching the object correspondence search process, the second process. In conclusion, we present a novel problem formulation and an algorithm to efficiently and accurately query label time series sensor data or sim-to-real validation. And our experiment demonstrates by utilizing the existing labeled big data set, the algorithm, we can query up to 3 orders of magnitude faster with higher accuracy. And regarding future research, some of the interesting questions is what tools can we build for researchers to explore and understand the data set they have using the query algorithm? So things that come to my mind is the following, such as, let's say a crash accident happens, Waymo had a crash, and then the Tesla looks at it and say, ooh, have you ever had that, have you encountered such situation before, and was our system okay? But we have terabytes or petabytes of data. Like, how do we actually go through all that? Can we do that algorithmically? Maybe we can use algorithms like this. But more importantly, research things that need to be researched is that what about the coverage? Like what types of scenarios, interactive scenarios do we have in our data set? And how can we start reasoning and aggregating the data set into different scenario level? Something to think. Thank you.
Any questions from the audience? Okay, I'll start with one, I guess. I'm gonna start from the last part, which was the experiments and the scalability results. I was wondering whether some way to decompose the problem, either spatially or temporally, could help you, obtain this months ago.
Yeah.
Scalability, and how do you think, we would approach?
Yeah, I mean, there's definitely limitations currently that needs to be improved regarding especially the object correspondence search and so on, which I think you're referring to. I think it can be, it's a tricky problem because we can't just simply look at, it's a tricky problem because we are requiring that m parameter m, which states that as long as the video contains that m length window of scenario that can match the scenario description, the temporal aspect, the behavioral aspect, then it's a check mark. But because of that, it's difficult to, which means, I mean, to expedite this matching process, you want to filter out the ones that are not potentially a candidate as early as possible. But because of that M aspect, it allows you to have other types of behaviors. So it's a tricky problem, which I need to ponder more about.
And do you think that some sort of a in-between approach where you provide the cynic programming language as input to these generative AI tools could maybe help them, address this issue a little bit more efficiently?
The object correspondence part. Yeah, I have thought about that too, but at the same time, it's gonna impact the query. That's one worry, because we want to enable this query against potentially large data set. But at the same time, if you start involving LLMs in between, that's gonna add latency to that query. That's
If we have no other questions, then let's go ahead and have the speaker. And for our last talk of the session, we have Camilo Rocha, who will be presenting to us work on extending event fee to support probabilistic concerns. It's interesting. Authority.
So thank you. This is the last talk of the day. It's been a long day, so let's thank you for being here at the talk. I'll try to cut to the chase and make it as quick as possible for 10 minutes. I want to relax a little bit. I'll be presenting the paper Algorithmic Analysis of MD in Rewriting Logic. This is joint work with Carlos Olarte, Camilo Florio, Carlos Ramirez, and let's get started. So why are we working on this? So the thing is that maybe you're aware that when you work with concurrent systems, most of the times it's very hard to prove that everything is fine. Like for every possible scenario, for every possible trace, things like that. So in safety critical systems, this is key. But sometimes you need to somehow loosen up that goal and try to prove things up to a threshold. And then this is where probabilistic systems kick in. So you have systems that are inherently probabilistic, or sometimes you want to make systems probabilistic so you can check them in different ways other than direct theorem proving. So how many of you are familiar with FNV? Can you raise your hands? Sort of people. So FNV is a framework based on set theory where you can model, simulate, and prove things, basically following a discrete, time steps, stuff like that. So you have full concurrency, you have theorem provers, you have SMT solvers integrated to it. And there is this key feature about refinement. So you can go from abstract systems to very concrete ones, right? And the idea here is to equip FNV with probabilistic simulations. So you can reason about these systems without going to a theorem proving part of FNV. And what we are using is rewriting logic, the semantic framework side of it, so we can encode FNV in rewriting logic and then use tools available to mod to do probabilistic simulation and a statistical model check. So what are the main contributions of this work? First, you get new algorithms and techniques to do probabilistic simulation and at the same time a statistical model checking of FNV specifications. There is also this semantics that's been extended. So there is a formal semantic of FNV, and then you extend this with probabilistic choice and concurrency, to speak, and this is being formalized and is executable in the mode rewriting logic engine. And the idea in the long run is to have different methods complement each other from the proof theoretic point of view and the algorithmic point of view. So we're contributing to the second part, the algorithmic viewpoint of the things. So this is the agenda. First, I'll be talking about MMB and rewriting logic, some very high level stuff so you can understand what's going on. Then I'm going to talk about two maps, the maps going from MMB machines to rewriting logic, MMB machines to rewriting logic with probabilities. And in the last part of the agenda, I'm going to be talking about some implementation details. But let's get started with MMB and rewriting logic. So this is the notation used for machines. I'm going to come back to it, but this is the specification unit in MMB. So the idea is that in MMB you have set theory at your formal basis and formal logic as well to specify properties of the system. And then you follow refinement steps up until you get a system you want to implement. So machines, they have basically different parts, and the goal is to specify the system as a machine. So you have a context. That's the static part of the context of the whole system. You have a set of variables that characterize the states of the system. They can change the values. You have invariants. In this case, initialization invariant that says how to instantiate the variables of the machine for the first time. Then you have a set of events, and you also have an initialization besides the invariant in some cases. So I want to move here. This is the way you specify a context in MMB. So you have the name of the context. You define different sets. You can define sets by enumeration. You can also define sets as subsets of the naturals, or you can basically define a type. And then you can have constants saying, well, the type and the name of the constant. This is very simple context for a very simple system that you can find in the paper. Then you have the machine seeing a context. So basically, you're importing the context, so you can have some parameters fixed for you, and then you can define variables. So this model has 4 variables: handle, year, door, and CMD commands. And there are some invariants, in this case, typing invariants for these variables. And you define initialization assignment for each one of the variables. It's very simple. You use you can think of the state of the system or the machine as a vector, and then you just basically say how the vector changes over the time. This is the part where it gets set for the by the initialization process. So these are the examples of 2 events. So you're basically having 2 parts: the guard part and the action part of the event. So here you're saying that if you certify this, I'm going to explain this in a bit, your handle goes to CC and the CMD increases by 1. As simple as that. So here you have a new keyword called weight. That has to be probabilities. I'm going to explain that in a second. It's a number that assigns a priority to the event. And then you have it's like an external parameter for any CC, can be up or down, doesn't matter. And whenever the CMD variable is at most CMD, then these things happen. And the same goes down here. The main difference between this event and this event is that this one has probabilistic assignment. And you can see that the weights are different. So the gear changes to extended with 90% or 90% of the times, and retracted to 10% of the times. These changes were proposed first by Audali a few years ago as an extension of MMB, right? And they give some semantics, proof theoretic semantics of how to deal with them. But up until now, there were no probabilistic simulation, backends, or for statistical checking analysis available to MMB. And this is the idea behind MMB with probabilities. Let's go to rewriting logic. Which of you are familiar with rewriting logic? 1, 2, 3. Very clear. So rewriting logic is a logic for concurrent systems. The idea is that you have a framework. I would say first of the logic framework, where you can specify 2 relations: equality and transitions, right? Rewrite theories are the objects of simplification, so to speak. And you have 2 parts in a rewrite theory: an equational part that defines the deterministic aspects of the system, data types, values, and stuff like that. And you have the rewrite part That's where you have concurrency. So you can interleave rewrite rules to a state. So you can have probabilistic semantics added to rewriting logic. So basically, if you want to look at it from the transition viewpoint, you have now transitions with weights that are probabilities, right? So you go from a LTS to a probabilistic LTS. That's the idea. So I'm not going to get into this, but the idea in general is that in order for this to have any meaning, you need to get rid of all concurrent transitions that are not guarded by probabilities. Every single concurrent transition needs to be guarded by probabilities for the simulation and for the statistical model checking part of it to make any sense. Otherwise, you won't have measurable sets, and then you can do any analysis. So that's the idea. Remove all non-determinism by guarding it with probabilities. This is a mathematical usual definition of a rewrite theory. So you have a signature, therefore the logic signature, sorts, function symbols, no predicate symbols. You have the equations and the axioms, and they are separated here because these are structural axioms of associativity, commutativity, and you make use of that so that your specifications are nicer and more general, and equations that in practice are used from left to right to reduce. And the rewrite rules that I just mentioned, they go from states to states, denoting transitions. In rewriting logic, you assume that rewriting the equations modulo the axioms is confluent and terminating. That means that whenever you have a term, you can assume that it has a canonical form and it's unique. And then on these canonical forms, you perform the rewrite steps. So what you are doing in the end is rewriting equivalence classes of terms with the rules. That's what you have here. And there's no assumption about termination, confluence, whatever, about the rewrite relation. Just very open. So let's go to the maps. So this is the idea. You start with a machine, 11B, and then you can have two rewrite theories from the same machine. The first one is a rewrite theory that you have where all concurrent behavior is enabled. You have true concurrency there. And this is done basically if you want to have simulation, state space exploration, reachability analysis, even LTL model checking. This is already available for FNB, for instance, from the Golan environment, but still you can now use this tool from the mod environment to perform analysis on machines. And the second map or transformation is the one capturing the probabilistic behavior of the system. So basically, what you can do with this is simulation in the probabilistic setting, and again, a statistical model checking against quacheck, which is a logic for probabilities in transition systems. So I'm going to give you a high-level description of these two maps or mappings. I'm going to start with the first one. So we use object-like notation in rewriting logic for specifying both context and machines of FMD. So the notation is basically you have an identifier, a class identifier, and a set of attributes. In this case, we're going to have two classes, the class context and the class machine. And in each case, you have these sets of attributes. So you have the constant sets of types you define them in the context, and the constants you define in the context. And in machine, you have variables and events. That's what you get from this map. And we're going to represent this by juxtaposition. So you have a context and a machine. Right. And events, this is the most interesting part of the transformation, because you have interlinear, so you have to support that. Basically, the way we did it was labeling events with one of these four possible states. So an event can be in state unknown, meaning that given a specific state, the condition of the event has not been evaluated, so you don't know if it is enabled or not. Then blocked, if the condition has been checked and is false. Execute with a wait, meaning that the condition has been checked and is true. and then it is assigned a priority W. This is going to be handled whenever it comes to the priority setting, and you have the label running when the event has been in state execute and has been chosen to be executed at one time step. These are the right rules, axiomatizing the transition of a machine from enable to execute. Basically, this condition is a blocking condition that says that if there is at least one event which is unknown, you cannot apply this rule. So basically, you're waiting for all the events in the system to be evaluated to either block or execute before applying this rule, right? And then you can go back from running. You have an event you have chosen for execution to a new state in which all the events go to a state unknown. So it's basically a quiescent step in which you block execution until all the conditions of the events have been evaluated, and then one of them is chosen, executed, and repeated again. That's what the process does. On the probabilistic side of things, the idea is this is what took us the most time. So we read this specification like 3 times because the way it was done before, basically you ended up with 2 different rewrite theories, and keeping out these theories synchronized was a problem. So we didn't want that. So in the end, what we had was a solution in which you only need to add metadata to some of the rewrite rules and keep the same specification for both the concurrent part and the probabilistic part of the transformation. So it's basically what you do. You annotate these rules with the priorities for each one of the events, and also for the probabilistic choice when you assign values. So in this case, this is the rule choosing pushes the next event to be executed. So it has a weight. And this is probabilistic choice of an element of a value, sorry, with probability P. And this is deterministic choice with probability 1.0, right? And we use this tool for in modern C that will read this metadata. I will execute the system with those values as probabilities. The good thing about this is that if it finds a rule or transitions that are not guarded by a probability distribution function, it will assume that's uniform, and then we'll execute this even that they did. You can also add different functions for different machines and executions. And this is what explains it. So in the end, what you do, you have the system, you execute this as many times in Monte Carlo runs until you reach the threshold you want to you set at the beginning for evaluating the given expression, and then you can see if the property holds or not for the system that they did. So we have two theorems, sorry. One for the non-deterministic part, the first map, and the other is for the probabilistic map. Definition 1 basically says that the machine has some conditions, only sees one context, and some equations are defined there. I don't want to get into that as explained in the paper, but basically it says that if you can go from state S to S prime using event B or applying event B in the machine, you can do this as well. The right theory we have developed. Theorem 2 says basically the same thing, but equipping the transition with probabilities, and this is also proven in the paper. And these 2 rules here are the rules that you showed with the annotation about the probabilities, the weights that you have to add. So basically, you have one only specification, and from that you get full concurrent behavior, and you get probabilistic behavior without any more changes. Okay. You can have a look at implementation. It's available at GitHub. There are 3 main directories there. The first one contains the supporting rewrite theories that define the maps and support the maps, so to speak. You can find a common prelude there for the data types that are available for the transformation. You have sets, relations, functions, projections, stuff like that. And you can find that in a file. And you can also find the right rules there and documentation of what they mean. In this directory, I'm going to come back to this part of the repository in the next slide. Basically, you find examples we have been working on. And here you find a parser that will take any FMB machine and will translate it into a syntax of the tool here, so you can make the transformation and try the example you may have. So this is a snapshot of what you can find in the repository. This is an example of case study of a retransmission protocol with probabilities. You can have lots of messages, I guess, if I remember properly, and you can see the setup and the results we have. This is just as I told you in a snapshot. So what can you find in the case studies? You will find maybe 5 or 6 examples taken from this book. This is the book we used to teach FMD in our school. Some of them have been modified with probabilities as well, so you can see the two maps in action. We also have an example of a social network, a small one, in which we use statistical model checking to see if it is possible to reach consensus in this network using different measures. And you can find that very detailed in the repository. And we have a controller for a learning system. That's the running example in the paper, and a P2P protocol. Right? You can check that, and there are instructions how to execute these things from zero. Conclude. So now you can have FMD models with probabilities simulating in FMD. So basically, this is transparent for the user. You get the FMD model, you apply the transformation, run the experiments, and then you can understand what's going on in your machine without any knowledge of model. The automatic, as I just told you. So implementing what you already have in FMD, for example, LTL model checking, you have a statistical model checking of what its properties. This is important because as far as we're aware of, it's very hard to theorem proving with probabilities, right? So if we complement this idea of developing software by construction being correct, and the idea is that statistical model checking will guide the design and implementation process of the systems. And we have some case studies in which we have validated the main ideas and the development of the mappings and the parsing. So what's left? The next thing we want to do is define a plugin for RAN, so people can use that, like without knowing all these things you have been looking at for the past 20 minutes. And we already have that with another plugin. So I think this is going to take us very little time to get a student to use for us. We need to extend support for richer types and operators and find more challenging examples. We're looking at some drivers that have been verified with FMD, and maybe we can work on them and report how this thing scales or not. And we want to explore for sure symbolic techniques. So when you have variables, this ending in the events, maybe you want to know what will happen regardless of the choice. So you can do symbolic execution on these FMD machines, and also use SMT solving for parameter synthesis. So conditions can be evaluated more easily from our viewpoint. And I think that's it. Thank you.
Great talk.
Any questions?
Thank you very much. Is there a way to see the refinement relation between machines through this mode encoding? If you have like two, I mean, like the usual approach where you refine a machine by new machines, can you observe or compute or check stuff with this encoding?
So if you have one refinement step, so to speak, you can apply the maps to each one of the steps and then see how different they are. But right now, there's no way of saying this behavior is because of the refinement or not. Basically, you get all in one package. I'm not sure if I'm saying correctly.
Like once you have your two modeling with rewriting logic in mode, can you compare or relate the two different encodings of two different machines that refine each other?
You may do that using by simulation or simulation, but it is not implemented as part of the transformation yet. So we're assuming that you get a model and you execute that. So if I understand properly, in this case, you need to have the two models, the initial one and the prime one, execute them both, test them, and then see if they comply and the requirement for particular image. We haven't done that in the tool yet.
Thanks.
Thank you, Camilo. I remember a couple of years ago, I read a paper integrating, I think, the Prism to EvenB. Do you know what that was and how does it compare with this approach?
So Prism is a statistical model checking as well. The difference between them, basically, the logic they verify. Quatex is more general to the logic supported by Prism, which is PCTL, if I remember properly. And because of it, you can have, for example, unbounded data structures with Quatex and PMC. If I remember properly, that's not possible with Prism. So basically, you get more freedom or expressiveness, but in the end, you can check many properties in similar properties.
I do have one question myself. I was wondering if what you currently have can support not deterministic choices between distributions. So in essence, being able to maybe describe MTPs, macro precision processes as event-based systems.
Maybe I didn't get so how to go from process to.
Yeah, so instead of considering a probabilistic choice, have a non-deterministic choice between probability distributions, which is the case for decision processes. Yeah, is that something that we currently support, or?
So far, what we have is that we either do all possible runs, so to speak. You can use every possible value, or you restrict the one you choose with probabilities. That's the two options we have right now. Nothing in between.
Okay then. Oh.
Can be a bit related to paranoid about the refinement. Yeah, I'm also interested in that part. And so maybe you have heard of the sorry, it's a comment rather than question, maybe question. But, so there are some studies on probabilistic so guarded command or probabilistic refinement calculus. So I imagine that if your approach can be extended to support such a refinement so checking mechanism, that can be interesting. So do you have any opinion on that?
Thanks for the suggestion. I wasn't aware of that. I didn't know we have refinement calculus, with probabilities. Yeah, I would like to look into it. So
sounds good.
It sounds nice because one of the strengths of MB is that you can do this refinement process iteratively. So that will match perfectly.
Okay. If there are no more questions, then let's thank the speaker.
Thank you.
Okay. Thanks everybody for coming. This concludes the second day of NFM. We'll start bright and early at 9 a.m. tomorrow morning. We hope to see you all then.